Picture this. You're flipping through a dusty paleontology textbook from the 1980s, and there it is, a bizarre creature that looks like someone crossed a vulture with a giraffe and gave it wings the size of a small airplane. Fast forward to today, and that same creature appears in documentaries looking completely different, sleek, majestic, and somehow both alien and familiar at the same time. What happened? How did our understanding of one of the most magnificent flying animals that ever lived transform so dramatically over the decades? Welcome to the fascinating journey of Quetzalcoatlus northropi, a pterosaur whose scientific story reads like a detective novel filled with locked museum vaults, mysterious bone fragments, and revolutionary discoveries that completely upended everything we thought we knew about these ancient giants. This isn't just another dinosaur documentary. This is the untold story of how science itself evolves, how our perceptions shift, and how a creature that lived 68 million years ago continues to surprise us today. But here's what makes this story absolutely incredible. For nearly 5 decades, one of the most famous prehistoric animals remained almost completely misunderstood. We're talking about an animal that dominated the skies at the end of the age of dinosaurs, yet its true nature was hidden behind a wall of scientific secrecy and fragmentary evidence that would make any mystery novelist jealous. The tale begins in the scorching badlands of Texas during the early 1970s. Picture paleontologists working under the relentless desert sun, carefully excavating what appeared to be the remnants of something extraordinary. What they uncovered were bone fragments so massive that they defied immediate comprehension. Wing bones that stretched longer than most people are tall, suggesting a flying animal of unprecedented proportions. These weren't just any fossils. These were the remains of what would eventually become known as Quetzalcoatlus northropi, named after the Aztec feathered serpent god Quetzalcoatl. The choice of name wasn't coincidental. This creature seemed to embody the mythical grandeur of ancient legends, a flying giant that ruled the prehistoric skies with an authority that seemed almost divine. However, the initial discovery presented paleontologists with a puzzle that would take decades to solve. The fossil remains consisted primarily of enormous wing bones and what appeared to be smaller, more complete skeletons. The logical assumption at the time was that these smaller specimens represented juvenile individuals of the same species. After all, it made perfect sense that baby Quetzalcoatlus would be significantly smaller than their colossal parents. But science rarely unfolds as neatly as we expect, and this assumption would prove to be just the first in a series of misconceptions that would shape decades of reconstructions and popular depictions. The fragmentary nature of the initial finds meant that paleontologists were essentially trying to reconstruct a jigsaw puzzle with most of the pieces missing. And some of the pieces they thought belonged to the puzzle actually came from entirely different boxes. Making matters infinitely more complicated was the institutional secrecy that surrounded these remarkable fossils. The museum that housed the specimens operated with a level of confidentiality that would make government agencies envious. Researchers who wanted to study the bones faced bureaucratic obstacles that seemed designed to discourage investigation rather than promote scientific understanding. Confidentiality agreements limited access, and restricted publication rights created an environment where scientific progress moved at a glacial pace. This institutional gatekeeping had profound consequences for how Quetzalcoatlus was understood and depicted during its early years. Without detailed anatomical studies, without comprehensive descriptions, and without the collaborative peer review that drives scientific advancement, early reconstructions of this magnificent creature were built on speculation rather than solid evidence. The first attempts to visualize Quetzalcoatlus reflected both the limitations of the available evidence and the preconceptions of the era. During the 1970s and early 1980s, pterosaurs were generally viewed through a lens heavily influenced by modern flying animals, particularly birds and bats. Scientists and artists attempted to fit Quetzalcoatlus into familiar categories, often with results that now seem almost comically inaccurate. Early depictions showed Quetzalcoatlus as a creature that seemed to embody the worst aspects of multiple animal groups. Imagine a pterosaur with the sinuous, serpentine neck of a snake, a head so tiny it seemed almost vestigial, and teeth sharp enough to tear through flesh like daggers. Many reconstructions gave it a small, insignificant crest and portrayed it as a creature that moved awkwardly underground, its massive wings serving as cumbersome appendages that hindered terrestrial locomotion. These early artistic interpretations weren't the product of poor imagination or lack of skill. They were the inevitable result of working with insufficient data. When you're trying to reconstruct an animal from fragments, every missing piece becomes a blank space that must be filled with educated guesses, comparative anatomy, and sometimes pure speculation. The inland environment where Quetzalcoatlus fossils were discovered added another layer of complexity to early interpretations. Most pterosaurs known at the time were associated with marine environments, living along coastlines and feeding on fish and other aquatic prey. But here was a pterosaur found in what had been an ancient terrestrial landscape, far from any prehistoric ocean. This geographic context led to one of the most persistent early theories about Quetzalcoatlus' behavior, the scavenger hypothesis. Scientists proposed that these massive pterosaurs functioned as the Cretaceous equivalent of vultures, soaring over vast inland territories and feeding on the carcasses of dead dinosaurs. It was an elegant theory that seemed to explain both the animal's enormous size and its presence in continental environments. The scavenger interpretation influenced artistic depictions for years, showing Quetzalcoatlus as a somewhat ungainly creature with the behavioral patterns of modern carrion feeders. These reconstructions often emphasized the animal's supposed reliance on soaring flight and portrayed it as spending most of its time airborne, scanning the landscape below for feeding opportunities. But even as the scavenger theory gained acceptance, nagging questions remained. The proportions didn't quite match what scientists expected from a specialized carrion feeder. The skull fragments that had been found suggested a different kind of anatomy, one that didn't perfectly align with the vulture-like lifestyle that many researchers envisioned. By the mid-1980s, the scientific community had made significant progress in understanding pterosaur relationships and classification. Quetzalcoatlus was placed within a family called Azhdarchidae, a group that included some of the largest and most distinctive pterosaurs known to science. Azhdarchids were characterized by several key features: exceptionally long necks, toothless beaks, and proportionally long legs that suggested a lifestyle quite different from other pterosaur groups. However, the classification of Quetzalcoatlus as an Azhdarchid created as many questions as it answered. The family itself was poorly understood during the 1980s and early 1990s, with most species known from fragmentary remains that made detailed anatomical studies virtually impossible. Scientists were essentially trying to understand one mystery by placing it within the context of several other mysteries. The limited understanding of Azhdarchids during this period led to reconstructions that, while more sophisticated than earlier attempts, still bore little resemblance to modern interpretations. Artists began depicting Quetzalcoatlus with the long neck characteristic of its family, but the overall proportions and posture remained largely speculative. Some reconstructions began to show Quetzalcoatlus with a more bird-like appearance, complete with sleek wings and streamlined body proportions. These depictions sometimes included speculative integument, coverings of primitive feathers or fur-like structures that gave the animal a more dynamic, living appearance rather than the reptilian skin that had characterized earlier reconstructions. Yet, even as these reconstructions became more refined and anatomically sophisticated, fundamental questions about Quetzalcoatlus remained unanswered. How did it move on the ground? What did it eat? How did it launch itself into flight? These questions would continue to puzzle paleontologists for decades, leading to a series of theories and counter-theories that would dramatically reshape our understanding of these remarkable animals. Mystery deep, the fragments that had been discovered in Texas around fossilized Jaween, as paleontologists began examining the same time as the original Quetzalcoatlus remains, these jaw pieces seem to tell a different story about the animal's anatomy and feeding habits. The fossils suggested a creature with a chunky, robust skull structure and what appeared to be a blunt, powerful beak, features that didn't quite match the emerging understanding of Azhdarchid anatomy. For years, these jaw fragments were incorporated into Quetzalcoatlus reconstructions, leading to depictions that showed the pterosaur with a heavy, almost crocodilian head structure. Artists and scientists alike struggled to reconcile this robust skull anatomy with the increasingly refined understanding of the animal's overall body proportions. The result was a series of reconstructions that seemed anatomically inconsistent, showing a creature with a delicate, elongated neck supporting a disproportionately massive head. This apparent contradiction highlights one of the fundamental challenges in paleontology: the tendency to assume that fossils found in the same location and geological formation necessarily belong to the same species. It's a logical assumption that often proves correct, but it can also lead researchers down false paths that take years or even decades to correct. The jaw fragment issue persisted through the late 1980s and into the 1990s, creating reconstructions that modern paleontologists would barely recognize. These depictions showed Quetzalcoatlus as a creature caught between different anatomical paradigms, part graceful, long-necked Azhdarchid, and part heavy-skulled, robust predator. The combination created an image of an animal that seemed almost chimeric, as if someone had attempted to merge two entirely different creatures into a single impossible form. Meanwhile, the smaller specimens that had been assumed to represent juvenile Quetzalcoatlus were beginning to reveal their own secrets as preparation techniques improved and more detailed analysis became possible. Subtle differences in anatomy became apparent. These weren't just smaller versions of the giant. They showed distinct characteristics that suggested they might represent something else entirely. The realization that these smaller specimens might not be juveniles came gradually, emerging through careful comparative studies and improved understanding of pterosaur development. Scientists began to notice features in the smaller specimens that didn't match what they would expect from young individuals of a giant species. The proportions were different. Certain anatomical features were more developed than expected in juveniles, and the overall morphology suggested a creature that had reached biological maturity despite its relatively modest size. This revelation would eventually lead to one of the most significant developments in Quetzalcoatlus research. But during the 1990s, it remained more of a nagging suspicion than a confirmed hypothesis. The scientific community was still grappling with the fundamental challenge of understanding these animals based on fragmentary remains and limited access to the most important specimens. As the 1990s progressed, new discoveries of Astarchid pterosaurs from other parts of the world began to provide crucial context for understanding Quetzalcoatlus. These discoveries included more complete specimens that revealed the true proportions and anatomy of large Astarchids. For the first time, scientists could see how these animals were actually constructed, how their long necks connected to their bodies, and how their wings were proportioned relative to their overall size. These new discoveries revolutionized reconstructions of Quetzalcoatlus, even though the animal itself remained known primarily from fragments. Artists began depicting the pterosaur with the sleek, sophisticated anatomy that characterized other Astarchids, a creature with impossibly long S-shaped neck, enormous wings that folded elegantly against its body, and proportions that suggested both power and grace. Some reconstructions during this period began to experiment with more speculative features, including primitive feathers or fur-like integumentary structures. These additions reflected growing evidence that pterosaurs possessed sophisticated body coverings that helped with thermoregulation and possibly display. The addition of these features transformed Quetzalcoatlus from a scaly reptilian creature into something more dynamic and bird-like, though still unmistakably alien in its overall appearance. The skim-feeding hypothesis emerged during this period as scientists struggled to understand how such massive flying animals could sustain themselves. The theory proposed that Quetzalcoatlus and other large Astarchids fed by flying low over bodies of water and skimming fish from the surface using their lower jaws. It was an elegant solution that seemed to explain both the animals' massive size and their distinctive anatomy. Skim-feeding reconstruction showed Quetzalcoatlus as a creature perfectly adapted for this feeding strategy. With a long, narrow beak ideally suited for slicing through water and specialized neck musculature that could absorb the shock of high-speed water contact. These depictions often showed the pterosaur in dynamic flight poses, wings spread wide as it glided mere inches above prehistoric lakes and rivers. The skim-feeding theory gained significant traction in the scientific community and popular media, influencing documentaries, museum displays, and educational materials throughout the late 1990s and early 2000s. It provided a compelling narrative that seemed to explain the evolution of gigantic flying animals in terms of specialized feeding ecology. However, even as the skim-feeding hypothesis gained acceptance, some researchers harbored doubts about its validity. The biomechanical requirements for skim feeding at the scale of Quetzalcoatlus seemed problematic. The forces involved in dragging a massive beak through water while maintaining flight would be enormous, potentially beyond the structural limits of even the most robust pterosaur anatomy. These concerns led to detailed biomechanical studies that examined whether large pterosaurs could actually engage in skim-feeding behavior without suffering catastrophic structural failure. The research involved complex calculations of wing loading, neck strength, and the hydrodynamic forces that would be generated during skim-feeding maneuvers. The results of these studies would prove devastating to the skim-feeding hypothesis, but that revelation was still years away. Throughout the late 1990s and early 2000s, Quetzalcoatlus continued to be depicted as a specialized aquatic forager, a creature that dominated prehistoric waterways through its unique feeding adaptations. Meanwhile, the institutional secrecy that had shrouded the original Quetzalcoatlus specimens for decades continued to limit scientific progress. Promises of detailed descriptions and comprehensive studies had been made repeatedly since the 1980s, but the most important fossils remained largely inaccessible to the broader scientific community. This situation created a bizarre scenario where one of the most famous prehistoric animals remained scientifically undescribed despite decades of public fascination and media attention. The lack of detailed scientific description meant that reconstructions of Quetzalcoatlus remained largely speculative, based on comparisons with better-known relatives and educated guesses about anatomy and proportions. This speculative foundation would prove problematic as new evidence emerged that challenged fundamental assumptions about these remarkable animals. The early 2000s brought new discoveries and analytical techniques that would begin to unravel many of the misconceptions that had shaped decades of Quetzalcoatlus reconstructions. Advanced imaging technologies allowed researchers to examine fossils in unprecedented detail, revealing anatomical features that had been invisible to earlier investigators. These technological advances, combined with new discoveries of Ajdar-Shid pterosaurs from around the world, began to paint a very different picture of how these animals lived and behaved. The emerging evidence suggested that everything scientists thought they knew about Quetzalcoatlus might need to be reconsidered from the ground up. The year 2007 marked a pivotal moment in the Quetzalcoatlus saga, one that would shatter decades of accepted wisdom and force scientists to completely reimagine how these colossal creatures lived their lives. A groundbreaking biomechanical study emerged that would demolish the skim-feeding theory once and for all, leaving researchers scrambling to rebuild their understanding of Ajdar-Shid ecology from scratch. The study's conclusions were as definitive as they were shocking. No pterosaur, regardless of size or anatomical specialization, could have survived the physical stresses involved in skim feeding. The forces generated by dragging a beak through water at flight speed would have been catastrophic, literally tearing the animal's head from its body. The elegant aquatic forager that had graced museum displays and documentaries for years was revealed to be a biomechanical impossibility. But if these giants weren't skimming fish from ancient waterways, what were they doing? The answer that emerged would prove even more fascinating than the discredited skim-feeding hypothesis. Scientists began to envision Ajdarchids as primarily terrestrial predators, creatures that spent much of their time stalking across prehistoric landscapes on foot, using their enormous size and powerful beaks to dominate ground-based ecosystems. This terrestrial interpretation transformed every aspect of how Quetzalcoatlus was depicted and understood. Instead of graceful aquatic specialists, these pterosaurs were reimagined as the apex predators of their terrestrial environments. Picture a creature the size of a giraffe stalking across the landscape on four legs, its massive wings folded against its body, scanning the ground for prey with eyes positioned high atop an impossibly long neck. The comparison to modern storks became a popular analogy among researchers. Like these familiar wading birds, Ajdarchids were envisioned as opportunistic predators that used their long necks and powerful beaks to capture whatever prey was available. But unlike storks, which are limited by their relatively modest size, Quetzalcoatlus could tackle prey items that would dwarf anything a modern bird could handle. This new terrestrial interpretation required a complete rethinking of Ajdarchid anatomy and locomotion. Scientists had to figure out how a creature with wings spanning 30 feet or more could effectively move around on the ground. The answer lay in sophisticated analyses of limb proportions and joint mechanics that revealed these animals to be far more terrestrially adapted than anyone had previously imagined. The wing structure of Ajdarchids, it turned out, was perfectly suited for quadrupedal locomotion. The massive wing bones could support the animal's weight on the ground, while specialized joints allowed the wings to fold efficiently when not in use for flight. These weren't clumsy, ground-bound giants struggling with oversized wings. They were sophisticated predators equally at home, stalking prey on foot or soaring through ancient skies. The reinterpretation of Ajdarchid ecology also shed new light on their flight capabilities. Rather than being specialized for continuous soaring like modern seabirds, these pterosaurs were likely adapted for short-distance flights between hunting grounds. They could launch themselves into the air when needed, travel efficiently to new territories, and then return to their preferred terrestrial hunting mode. This flight pattern would have made perfect sense for animals living in the semi-arid environments where Quetzalcoatlus fossils have been found. The late Cretaceous landscape of what is now Texas was characterized by vast fern prairies punctuated by river systems and scattered forests. For a terrestrial predator, the ability to fly between these scattered resources would have been invaluable. The prey items available to a terrestrial Quetzalcoatlus would have been diverse and abundant. Young dinosaurs, small mammals, reptiles, amphibians, and even fish in shallow water would all have been potential targets for a predator armed with a beak longer than most people are tall. The semi-arid environment would have concentrated prey around water sources, creating ideal hunting opportunities for a mobile predator. But perhaps most intriguingly, scientists began to speculate about Quetzalcoatlus interactions with the largest herbivores of its time. The Texas formations where these pterosaurs have been found also preserve remains of Alamosaurus, massive sauropod dinosaurs that could reach lengths of over 60 feet. While adult sauropods would have been far too large for any pterosaur to tackle, their young would have represented tempting prey items for a sufficiently large and bold predator. Imagine the scene: a juvenile Alamosaurus, already the size of a large horse despite being only a fraction of its eventual adult size, wandering too far from the protective presence of its massive parents. From the sky descends Quetzalcoatlus, wings spread wide as it transitions from soaring flight to a controlled landing nearby. The pterosaur approaches on foot, its giraffe-like proportions allowing it to tower over its intended prey, before striking with lightning speed using its enormous beak. This predator-prey dynamic would have represented one of the most dramatic ecological interactions of the Mesozoic era, flying reptiles large enough to threaten baby dinosaurs that were themselves larger than most modern mammals. It's a scenario that stretches the imagination, yet remains entirely plausible, given what we now know about Azhdarchid anatomy and behavior. The terrestrial interpretation also helped explain some puzzling aspects of Quetzalcoatlus anatomy that had never quite made sense under earlier ecological models. The animal's proportionally long legs, for instance, were perfect for ground-based locomotion, but would have been unnecessary for a purely aerial lifestyle. Similarly, the robust construction of the wing bones made perfect sense for an animal that routinely used its wings as weight-bearing limbs during terrestrial locomotion. Even as these new ecological interpretations revolutionized understanding of Azhdarchid behavior, the fundamental taxonomic questions surrounding Quetzalcoatlus remained unresolved. The jaw fragments that had confused researchers for decades were finally subjected to detailed analysis, leading to a startling revelation that would reshape the entire story of these magnificent creatures. In 1996, careful study revealed that the chunky jawbones that had been attributed to Quetzalcoatlus for over 2 decades actually belonged to an entirely different pterosaur. This discovery eliminated one of the major sources of confusion in Quetzalcoatlus reconstructions, finally allowing scientists to envision the animal with the gracile skull proportions typical of other Azhdarchids. The removal of the misattributed jawbones was like removing a distorting lens from a telescope. Suddenly, the true anatomy of Quetzalcoatlus came into much sharper focus. Gone were the bizarre reconstructions showing massive heads perched atop delicate necks. In their place emerged depictions of a creature with proportions that made anatomical sense, a predator whose skull was perfectly adapted for its terrestrial hunting lifestyle. But the taxonomic revelations were far from over. Around the same time that the jawbone misattribution was resolved, scientists made another discovery that would add yet another layer of complexity to the Quetzalcoatlus story. The smaller specimens that had been assumed to represent juvenile individuals were finally recognized as something entirely different, a distinct species that deserved its own scientific name. This second species was christened Quetzalcoatlus lawsoni, honoring one of the paleontologists involved in the original discoveries. At roughly half the size of the giant Quetzalcoatlus northropi, this smaller pterosaur was still enormous by modern standards, with a wingspan that likely exceeded 20 feet. But compared to its colossal relative, Quetzalcoatlus lawsoni was practically diminutive. The recognition of two distinct Quetzalcoatlus species solved several puzzles that had plagued researchers for decades. The apparent variation in size and anatomy among the Texas specimens suddenly made perfect sense. They weren't representing different growth stages of a single species, but rather two related species that had lived in the same environment during the final years of the Cretaceous period. Quetzalcoatlus lawsoni also provided crucial anatomical information that had been missing from studies of its larger relative. Unlike the fragmentary remains of Quetzalcoatlus northropi, the fossils of the smaller species included more complete skeletal elements, including crucial skull material that revealed important details about Ajdarchid anatomy. For the first time, scientists could see clear evidence of the bony crest that adorned the skull of at least one Quetzalcoatlus species. This crest, while not as elaborate as those seen in some other pterosaur groups, added an important new dimension to reconstructions of these animals. The crest likely served multiple functions as a display structure for species recognition and sexual selection, as an attachment point for jaw muscles, and possibly as an aerodynamic aid during flight. The discovery of the skull crest also raised intriguing questions about the appearance of the larger Quetzalcoatlus northropi. Did both species possess similar crests, or were there significant differences in skull ornamentation between the two? Without more complete skull material from the giant species, these questions remained tantalizingly unanswered. As the new millennium progressed, technological advances in fossil preparation and analysis began to reveal previously hidden details about Quetzalcoatlus anatomy. High-resolution CT scanning allowed researchers to peer inside fossilized bones without damaging them, revealing internal structures that provided crucial information about the animal's biology and lifestyle. These scanning techniques revealed that Quetzalcoatlus possessed the sophisticated air sac system characteristic of pterosaurs, with hollow bones that reduced weight while maintaining structural strength. The extent of this pneumatization was remarkable. Even the largest bones contained intricate networks of air spaces that made these giants far lighter than their size would suggest. The pneumatic bone structure helped explain how such enormous animals could achieve powered flight. Despite their massive wingspans, Quetzalcoatlus species were likely much lighter than equivalent-sized modern birds, allowing them to generate sufficient lift for takeoff and sustained flight. This revelation put to rest lingering doubts about whether the largest pterosaurs were truly capable of active flight or were limited to gliding. Advanced imaging also revealed details about the muscle attachment sites on Quetzalcoatlus bones, providing insights into the power and coordination of the flight apparatus. The wing bones showed evidence of massive muscle attachments, particularly in the areas responsible for the powerful downstroke that generates lift during takeoff. These anatomical features painted a picture of animals with formidable flight muscles capable of launching their massive bodies into the air. The flight mechanics of Quetzalcoatlus became a subject of intense study and debate among biomechanics experts. Computer modeling suggested that these giants used unique launch mechanism, employing their powerful forelimbs to catapult themselves into the air in a manner unlike any modern flying animal. This quadrupedal launch would have allowed them to generate the initial velocity needed to achieve flight despite their enormous size. Once airborne, Quetzalcoatlus likely relied heavily on thermal currents and updrafts to maintain altitude and travel long distances with minimal energy expenditure. Like modern vultures and condors, these pterosaurs were probably accomplished soarers, capable of remaining aloft for hours while scanning vast territories for feeding opportunities. The combination of terrestrial hunting abilities and long-distance flight capabilities would have made Quetzalcoatlus an incredibly effective predator. They could hunt systematically across their territory on foot, then fly to new areas when local prey became scarce or when environmental conditions changed. This mobility would have been particularly valuable in the seasonal environments of the late Cretaceous. Despite these advancing insights into Quetzalcoatlus biology and behavior, one crucial element remained frustratingly elusive: a comprehensive scientific description of the original specimens. For decades, the scientific community had been promised detailed publications that would finally reveal the full anatomical secrets of these remarkable animals. The institutional barriers that had limited access to the fossils for so long continued to impede progress well into the 21st century. Researchers from around the world who wanted to study the specimens faced bureaucratic obstacles that seemed designed more to protect institutional prestige than to advance scientific understanding. The situation became a source of considerable frustration within the paleontological community. Meanwhile, popular depictions of Quetzalcoatlus continued to evolve based on the fragmentary information that was available and comparisons with better-known relatives. Documentary filmmakers and museum exhibit designers struggled to create accurate reconstructions without access to detailed anatomical data, leading to depictions that varied wildly in their interpretation of the animal's appearance and behavior. Some reconstructions emphasized the predatory aspects of the terrestrial interpretation, showing Quetzalcoatlus as a fearsome stalker of prehistoric landscapes. Others focused on the majesty of its flight capabilities, depicting the pterosaur soaring gracefully above Cretaceous vistas. Still others attempted to capture the alien nature of these creatures, emphasizing features that had no modern equivalent. The lack of definitive anatomical information also meant that fundamental questions about Quetzalcoatlus remained contentious within the scientific community. How exactly did these animals move on the ground? What was their preferred prey? How did their flight mechanics differ from those of smaller pterosaurs? These debates would continue to simmer for years, awaiting the detailed anatomical studies that seemed perpetually just beyond reach. As the 2010s arrived, pressure mounted within the scientific community for the long-promised detailed descriptions of Quetzalcoatlus to finally see the light of day. Younger researchers who had grown up hearing about these magnificent creatures were eager to study them firsthand, while older scientists worried that crucial information might be lost if the specimens remained indefinitely inaccessible. The advent of new analytical techniques and imaging technologies made the delay even more frustrating. Tools that could have revolutionized understanding of Quetzalcoatlus anatomy were readily available, but they couldn't be applied to specimens that remained locked away from researchers. The scientific potential of these fossils was being squandered by institutional inertia. This period also saw the emergence of new Quetzalcoatlus relatives from fossil sites around the world. Discoveries in Romania, Jordan, and other locations revealed the global distribution and remarkable diversity of large azhdarchids during the final years of the Mesozoic. These new species provided crucial comparative data that helped refine understanding of Quetzalcoatlus anatomy and ecology, even as the original specimens remained largely inaccessible. The accumulating evidence from these related species suggested that the azhdarchid family had achieved remarkable success during the late Cretaceous, with giant species dominating terrestrial ecosystems across multiple continents. Quetzalcoatlus was not an isolated evolutionary experiment, but rather part of a worldwide radiation of giant pterosaurs that had found a successful ecological niche as terrestrial apex predators. This global perspective on azhdarchid evolution added new dimensions to interpretations of Quetzalcoatlus biology. These were not just isolated Texas giants, but representatives of a successful evolutionary strategy that had spread across the world. The implications for understanding late Cretaceous ecosystems were profound. Giant flying reptiles had apparently carved out ecological roles that would later be filled by large mammalian predators after the extinction of the pterosaurs. The growing body of evidence from related species around the world began to paint an increasingly detailed picture of what azhdarchid life might have looked like during the twilight of the dinosaur age. Scientists could now envision vast continental landscapes dotted with these colossal predators, each species adapted to the specific environmental challenges of their particular region, while sharing the fundamental body plan that made terrestrial gigantism possible. But as the scientific community grew increasingly impatient with the continued inaccessibility of the original Quetzalcoatlus material, something remarkable was happening behind the scenes. The institutional barriers that had protected these specimens for so long were finally beginning to crumble, not through external pressure alone, but through the dedicated efforts of researchers who understood the immense scientific value of finally unlocking these paleontological treasures. The breakthrough came in the most unexpected way imaginable. After nearly 5 decades of promises, delays, and bureaucratic obstacles. The year 2021 witnessed something that many in the paleontological community had begun to believe would never happen. The publication of detailed scientific descriptions of Quetzalcoatlus that would transform our understanding of these magnificent creatures forever. The release of these long-awaited studies represented more than just the end of an institutional embargo. It marked the beginning of a new era in Quetzalcoatlus research. For the first time since the initial discovery in the 1970s, scientists around the world could access detailed anatomical information about these remarkable animals, opening doors to research possibilities that had been locked away for generations. The impact of finally having access to comprehensive anatomical data cannot be overstated. Suddenly, decades of speculation and educated guesswork could be replaced with hard scientific evidence. The reconstructions that had been based on fragmentary information and comparisons with distant relatives could now be refined using actual Quetzalcoatlus anatomy, leading to depictions that were more accurate and more spectacular than anything that had come before. The detailed anatomical studies revealed a creature that was simultaneously more alien and more magnificent than previous reconstructions had suggested. The proportions were unlike anything in the modern world. A terrestrial giant whose neck alone stretched longer than the entire body of most large mammals, supporting a skull equipped with a beak that could have easily accommodated a human head within its length. But perhaps most remarkably, the new anatomical data confirmed many of the theoretical predictions that researchers had made based on biomechanical modeling and comparisons with related species. The limb proportions were indeed perfectly adapted for terrestrial locomotion, with modifications that allowed these giants to move efficiently on the ground despite their enormous size and the encumbrance of massive wings. The wing structure revealed by the detailed studies was a masterpiece of biological engineering. The bones were hollow, yet incredibly strong, with internal struts and supports that provided maximum strength while minimizing weight. The wing membrane attachment sites showed evidence of sophisticated muscular control systems that would have allowed precise manipulation of wing shape during flight, enabling these giants to extract maximum efficiency from every air current and thermal. The skull anatomy proved to be particularly revealing, showing adaptations that perfectly supported the terrestrial predator lifestyle that scientists had hypothesized. The beak was not just large, but specifically shaped for grabbing and manipulating prey on the ground. The eye sockets were positioned to provide excellent downward vision while the animal was standing upright, perfect for spotting potential prey items from the commanding height of a 6-meter-tall neck. The neck itself was revealed to be a marvel of vertebral engineering. The individual vertebrae were elongated and reinforced in ways that allowed the neck to support its own weight while remaining flexible enough for precise positioning during feeding. The muscle attachment sites suggested a neck that was both incredibly strong and remarkably agile, capable of striking with lightning speed when prey was within range. But the anatomical revelations went beyond just confirming existing theories about Quetzalcoatlus' lifestyle and behavior. The detailed studies also revealed unexpected features that suggested these animals were even more sophisticated than anyone had imagined. Evidence of complex air sac systems throughout the skeleton showed that Quetzalcoatlus possessed respiratory efficiency that rivaled or exceeded that of modern birds, explaining how such massive animals could sustain the metabolic demands of powered flight. The bone texture and growth patterns visible in the fossils provided insights into the development and lifespan of these remarkable creatures. Unlike the rapid growth seen in many dinosaurs, Quetzalcoatlus showed evidence of more measured development, suggesting that reaching full adult size was a process that took many years and required surviving the challenges of an increasingly dangerous world. The confirmation of Quetzalcoatlus lawsoni as a distinct species added crucial depth to our understanding of Azhdarchid diversity and evolution. The smaller species wasn't simply a scaled-down version of its giant relative, but showed unique anatomical features that suggested different ecological specializations within the same general terrestrial predator lifestyle. The skull crest of Quetzalcoatlus lawsoni, now visible in unprecedented detail, revealed itself to be a complex structure that likely served multiple functions. Beyond its obvious role in species recognition and display, the crest showed muscle attachment sites that suggested it played an important role in bite mechanics, helping to anchor the powerful jaw muscles that drove the massive beak. The size difference between the two Quetzalcoatlus species also provided important insights into Azhdarchid ecology and resource partitioning. Rather than competing directly for the same prey items, the two species likely specialized in different size classes of potential food, with the smaller lawsoni targeting prey that would have been beneath the notice of the giant northropi, while avoiding direct competition with its colossal relative. This ecological separation would have been crucial for the success of both species in the same environment. The late Cretaceous ecosystems of Texas were rich and diverse, but they were also highly competitive, with numerous predatory dinosaurs occupying various ecological niches. The ability of two closely related pterosaur species to coexist successfully suggests sophisticated resource partitioning that minimized direct competition. The detailed anatomical studies also shed new light on the flight capabilities of these remarkable animals. The wing loading calculations, now based on actual anatomical measurements rather than estimates, confirmed that both Quetzalcoatlus species were indeed capable of powered flight despite their enormous size. However, the flight style that emerged from the biomechanical analyses was quite different from earlier speculations. Rather than being primarily soaring animals like modern vultures or condors, Quetzalcoatlus species appeared to be adapted for what researchers termed short hop flight patterns. These giants could launch themselves into the air when needed, fly efficiently for moderate distances, and then return to terrestrial hunting mode. This flight style would have been perfect for animals that spent most of their time hunting on foot, but needed the ability to move between feeding areas or escape from dangerous situations. The launch mechanics revealed by the anatomical studies were particularly fascinating. The forelimb bones showed massive muscle attachment sites that would have allowed these animals to catapult themselves into the air using a quadrupedal launch technique unlike anything seen in modern flying animals. The power required for this launch was enormous, but the anatomical evidence suggested that Quetzalcoatlus possessed more than enough muscular strength to achieve takeoff even from level ground. Once airborne, the flight mechanics would have been dominated by the enormous wingspan and sophisticated wing control systems. The ability to adjust wing camber and angle of attack with precision would have allowed these giants to extract maximum lift from air currents and thermals, enabling them to remain aloft with minimal energy expenditure despite their massive size. The implications of these new anatomical insights extended far beyond just understanding Quetzalcoatlus itself. These creatures represented the culmination of Pterosaur evolution, the largest and most sophisticated flying animals that had ever existed. Their success as terrestrial predators suggested that the evolutionary potential of pterosaurs was far greater than previously imagined. The late Cretaceous world that Quetzalcoatlus inhabited was a place of extraordinary diversity and complexity. Massive, herbivorous dinosaurs dominated the landscape, while smaller predators filled numerous ecological niches. Into this already crowded ecosystem came the Azhdarchids, carving out their own unique role as aerial terrestrial giants that combined the mobility of flight with the predatory advantages of large ground-based hunters. The success of this ecological strategy was remarkable. Azhdarchids spread across the globe during the final years of the Mesozoic, with giant species known from North America, Europe, Asia, and Africa. Each continent developed its own distinctive Azhdarchid fauna, but all shared the fundamental adaptations that made terrestrial gigantism possible in flying reptiles. The global distribution of giant Azhdarchids also raised intriguing questions about their evolutionary origins and dispersal patterns. Did this body plan evolve once and then spread around the world through migration, or did similar ecological pressures lead to convergent evolution of giant terrestrial pterosaurs on different continents? The anatomical evidence suggested elements of both processes, with clear evolutionary relationships between species combined with regional adaptations to local conditions. The environmental context in which Quetzalcoatlus lived was crucial to understanding their success as terrestrial predators. The late Cretaceous climate was warm and humid, supporting lush vegetation that could feed enormous herds of herbivorous dinosaurs. These herbivore populations, in turn, supported a complex predatory ecosystem that included not only dinosaurian predators, but also the giant Azhdarchids. The landscape itself was also important. The semi-arid fern prairies of late Cretaceous Texas were punctuated by river systems and scattered forests, creating a mosaic of habitats that would have provided diverse hunting opportunities for versatile predators like Quetzalcoatlus. The ability to fly between these different habitat patches would have been invaluable for animals that needed to track seasonal changes in prey abundance and distribution. The prey items available to Quetzalcoatlus would have been remarkably diverse. Small dinosaurs, mammals, reptiles, amphibians, and fish would all have been potential targets for these adaptable predators. The enormous size of the giant species would have allowed them to tackle prey items that were beyond the reach of smaller predators, including juvenile representatives of the massive herbivorous dinosaurs that dominated late Cretaceous ecosystems. The hunting strategies employed by Quetzalcoatlus likely varied depending on the prey being targeted and the environmental conditions. The long neck would have been perfect for striking at prey while maintaining a safe distance, while the powerful beak could deliver devastating attacks to creatures much smaller than the pterosaur itself. The combination of terrestrial stalking ability and aerial mobility would have made these predators incredibly effective at locating and capturing prey across vast territories. But even as our understanding of Quetzalcoatlus biology and ecology reached unprecedented levels of detail and sophistication, new questions emerged that highlighted just how much we still don't know about these remarkable creatures. The social behavior of Azhdarchids remained largely mysterious. Did these giants live solitary lives, or did they interact with their own kind in complex ways? The evidence for social behavior in Quetzalcoatlus was tantalizing but inconclusive. The fact that two closely related species coexisted in the same environment suggested some level of species recognition and behavioral differentiation. But whether this extended to complex social interactions within species remained unclear. The skull crests that adorned at least some Azhdarchids were clearly display structures, but how they were used in social contexts remained a matter of speculation. The developmental biology of these giants also raised fascinating questions that the anatomical studies could only partially address. How long did it take for a Quetzalcoatlus to reach full adult size? What were the growth rates and metabolic requirements during development? How did juveniles survive in ecosystems dominated by large predators while they were still too small to defend themselves effectively? The bone histology visible in the fossils provided some clues about growth patterns, but many questions remained unanswered. The evidence suggested that reaching full adult size was a gradual process that took many years, but the details of this development remained frustratingly elusive. Understanding Azhdarchid development was crucial for comprehending how these remarkable animals achieved their enormous size while maintaining the ability to fly. The extinction of Quetzalcoatlus and other Azhdarchids at the end of the Cretaceous period represented one of the most significant losses in the history of vertebrate flight. These animals had achieved a level of aerial gigantism that has never been equaled before or since, yet they vanished completely along with the non-avian dinosaurs when the Mesozoic era came to its catastrophic end. The reasons for Azhdarchid extinction were likely complex and multifaceted, involving the same environmental catastrophe that ended the reign of the dinosaurs. The impact winter that followed the asteroid collision would have disrupted the food webs that supported these giant predators, while the collapse of terrestrial ecosystems would have eliminated the prey base that Azhdarchids depended upon for survival. The loss of the Azhdarchids marked the end of an evolutionary experiment that had pushed the boundaries of what was possible in flying animals. Never again would the skies be dominated by predators of such enormous size and sophisticated capabilities. The ecological niche that they had carved out as aerial terrestrial giants remained unfilled after their extinction, representing one of the many ecological roles that disappeared forever at the end of the Mesozoic. Yet, despite their extinction, the legacy of Quetzalcoatlus and its relatives continues to inspire and amaze us today. These creatures represent the pinnacle of pterosaur evolution, demonstrating that the reptilian approach to powered flight was capable of achieving sizes and capabilities that rival or exceed anything seen in the modern world. They remind us that the history of life on Earth includes chapters of diversity and magnificence that far exceed anything in our contemporary experience. The story of how our understanding of Quetzalcoatlus has evolved over the past 5 decades also serves as a powerful reminder of how science progresses. The journey from the fragmentary, misunderstood creature of the 1970s to the sophisticated, well-documented predator revealed by modern studies illustrates both the challenges and the triumphs of paleontological research. Each phase of this scientific journey built upon previous work while correcting earlier misconceptions and adding new layers of understanding. The process was neither linear nor predictable, involving false starts, institutional obstacles, and paradigm shifts that completely transformed our view of these remarkable animals. Yet, through it all, the persistent efforts of researchers around the world gradually assembled a coherent picture of what Quetzalcoatlus was really like. The technological advances that made this progress possible, from improved fossil preparation techniques to sophisticated biomechanical modeling, demonstrate how paleontology continues to benefit from developments in other fields of science and engineering. The CT scanners that revealed internal bone structure, the computer models that tested flight mechanics, and the analytical techniques that resolved taxonomic questions all contributed to our evolving understanding of these ancient giants. But perhaps most importantly, the Quetzalcoatlus story illustrates the crucial role that institutional cooperation and open scientific communication play in advancing our understanding of the natural world. The decades of limited access to crucial specimens slowed progress significantly, while the eventual release of detailed anatomical data accelerated discoveries at an unprecedented pace. The lessons learned from the Quetzalcoatlus research program extend far beyond paleontology itself. In an age when scientific collaboration and data sharing are increasingly important for addressing complex global challenges, the Pterosaur studies serve as both a cautionary tale about the costs of institutional secrecy and an inspiring example of what becomes possible when barriers to scientific cooperation are finally removed. As we look toward the future of Quetzalcoatlus research, the possibilities seem almost limitless. The detailed anatomical data that became available in 2021 has opened numerous new avenues of investigation, from sophisticated biomechanical studies to detailed ecological modeling. New analytical techniques continue to emerge that can extract additional information from existing fossils, while ongoing fieldwork may yet reveal new specimens that will further refine our understanding. The integration of Quetzalcoatlus studies with broader research into late Cretaceous ecosystems promises to reveal new insights into how these remarkable predators fit into their ancient world. Climate modeling, vegetation reconstructions, and studies of contemporary fauna will all contribute to a more complete picture of the environmental context in which these giants lived and thrived. Advanced imaging techniques continue to reveal new details about Quetzalcoatlus anatomy and biology. Synchrotron scanning, neutron tomography, and other cutting-edge technologies can extract information from fossils that was previously invisible to researchers. Each new technique has the potential to unlock additional secrets about these remarkable creatures. The story of Quetzalcoatlus northropi, from mysterious fragments to sophisticated predator, represents one of the most dramatic transformations in our understanding of any prehistoric animal. It demonstrates that even the most famous fossils can continue to surprise us, that scientific paradigms can shift dramatically as new evidence emerges, and that the history of life on Earth continues to reveal wonders that exceed our wildest imagination. This magnificent pterosaur, named after an Aztec god and revealed through decades of patient scientific investigation, stands as a testament to both the incredible diversity of ancient life and the persistent curiosity of the researchers who work to understand it. The creature that once seemed impossible, a flying predator larger than a giraffe, has been revealed as not only possible, but brilliantly adapted to its role as one of the most successful predators in Earth's history. As we stand at this remarkable juncture in paleontological history, with decades of mystery finally yielding to scientific scrutiny, the transformation of Quetzalcoatlus from enigma to understanding represents something far more profound than just another fossil description. This is a story about how knowledge evolves, how preconceptions crumble, and how the most extraordinary creatures that ever lived continue to challenge everything we think we know about the possibilities of life itself. The detailed studies that emerged in 2021 didn't just fill in missing anatomical details, they revolutionized our entire conception of what these animals represented in the grand tapestry of evolutionary history. For the first time, scientists could examine actual bone surfaces, trace muscle attachment sites, and analyze growth patterns with the kind of precision that had been impossible during the decades of limited access. What emerged from this unprecedented level of detail was a creature that defied easy categorization or comparison with anything in the modern world. The skeletal architecture revealed by high-resolution imaging showed adaptations that were simultaneously familiar and utterly alien. The wing bones displayed the hollow construction typical of flying animals, but their sheer scale pushed the boundaries of what seemed physically possible. Individual wing elements stretched longer than entire modern birds, yet maintained the delicate internal structure necessary for powered flight. The vertebral column told its own remarkable story of evolutionary innovation. Each neck vertebra was a masterpiece of biological engineering, elongated far beyond the proportions seen in any modern animal, yet reinforced with complex systems of pneumatic spaces and structural supports. The cervical ribs formed intricate networks of bracing that allowed this impossibly long neck to function as both a flexible feeding apparatus and a rigid support structure when needed. But perhaps most striking was the evidence for the sophisticated sensory systems that would have been necessary for a terrestrial giant to function effectively. The skull anatomy revealed enlarged areas for brain tissue, suggesting cognitive capabilities that went far beyond simple predatory reflexes. The eye sockets were positioned and proportioned in ways that would have provided exceptional visual acuity across a wide field of view, perfect for a predator that needed to spot potential prey from the commanding height of a 6-meter-tall hunting platform. The inner ear structures, preserved in exquisite detail, showed adaptations for maintaining balance and spatial orientation that would have been crucial for an animal transitioning between terrestrial and aerial locomotion. These weren't just flying reptiles that happened to walk on the ground occasionally. They were sophisticated predators, equally adapted to both terrestrial stalking and aerial travel, switching between these modes with a fluidity that has no modern parallel. The muscle attachment sites visible on the bones painted a picture of raw power that was almost difficult to comprehend. The flight muscles alone would have been massive, generating the enormous forces necessary to lift a creature weighing hundreds of kilograms into the air from a standing start. But equally impressive were the terrestrial locomotion muscles. The attachments for the muscles that controlled ground movement showed that these animals possessed the strength and coordination necessary to move efficiently despite their enormous size and unusual proportions. The biomechanical analyses that became possible with access to detailed anatomical data revealed flight capabilities that exceeded even the most optimistic earlier estimates. Computer modeling showed that Quetzalcoatlus could not only achieve powered flight, but could do so with remarkable efficiency. The wing design was perfectly optimized for extracting maximum lift from air currents while minimizing the energy costs of remaining airborne. The launch mechanics proved to be particularly sophisticated, involving a coordinated sequence of movements that began with the animal crouching on all fours, building tension in the massive flight muscles, and then explosively extending both the hind limbs and forelimbs to catapult the entire body into the air. This quadrupedal launch technique generated far more initial velocity than any bipedal takeoff could have achieved, solving the fundamental problem of how such massive animals could overcome the tyranny of scale that limits the size of flying creatures. Once airborne, the flight style that emerged from biomechanical modeling was unlike anything seen in modern flying animals. Rather than the continuous flapping flight of birds or the pure soaring of vultures, Quetzalcoatlus appeared to employ a hybrid strategy that combined powerful initial acceleration with efficient gliding phases. This flight pattern would have been perfect for an animal that needed to cover substantial distances quickly, but didn't necessarily need to remain airborne for extended periods. The ecological implications of these refined flight capabilities were staggering. A terrestrial predator that could also fly efficiently between hunting grounds would have enjoyed advantages that no purely ground-based predator could match. Seasonal changes in prey distribution, temporary food shortages, or dangerous encounters with other predators could all be addressed by simply taking to the skies and relocating to more favorable hunting territories. The detailed anatomical studies also revealed evidence for sophisticated thermoregulatory adaptations that would have been crucial for such large animals. The bone structure showed extensive pneumatization that would have improved heat exchange efficiency, while the surface textures suggested attachment points for elaborate integumentary structures, possibly including primitive feathers or fur-like coverings that would have helped maintain optimal body temperature. This evidence for complex body coverings added yet another dimension to reconstructions of these remarkable creatures. Instead of the scaly reptilian skin that had characterized earlier depictions, modern reconstructions began to show Quetzalcoatlus with sophisticated integumentary structures that gave them a more dynamic, almost mammalian appearance while retaining their fundamentally reptilian anatomy. The feeding apparatus revealed by the detailed studies was particularly impressive in its sophistication. The beak wasn't just large, it was precisely engineered for maximum effectiveness as a predatory tool. The tip was reinforced for penetrating tough skin and muscle, while the sides showed adaptations for gripping and manipulating prey. The jaw joint was positioned to maximize bite force while maintaining the precision necessary for capturing smaller prey items. The neck musculature attachments revealed a striking system that could generate lightning-fast strikes across a remarkable range of motion. The animal could strike downward at prey near its feet, sweep sideways to capture fleeing animals, or extend forward to reach prey at considerable distances, all while maintaining the strength necessary to subdue struggling victims that might weigh hundreds of kilograms. But the most remarkable aspect of the feeding system was its versatility. The same apparatus that could deliver devastating attacks to large prey could also be used with surgical precision for capturing smaller animals. This adaptability would have been crucial for a predator living in environments where prey availability could vary dramatically with seasonal changes and environmental conditions. The prey spectrum that would have been available to Quetzalcoatlus was extraordinary in its diversity. The late Cretaceous ecosystems of North America supported an almost unimaginable variety of potential food sources. Small mammals scurried through the underbrush, primitive birds nested in the scattered trees, and countless reptiles and amphibians inhabited the wetland margins. But most spectacular of all were the dinosaurs themselves. From tiny chicken-sized species to juveniles of the massive sauropods that could still be larger than modern elephants despite being only a fraction of their eventual adult size. The hunting strategies that would have been available to such versatile predators boggled the imagination. A Quetzalcoatlus could spend hours stalking through fern prairies on foot, using its elevated vantage point to scan vast areas for movement that might betray the presence of prey. When targets were spotted, the long neck could strike with cobra-like speed, delivering precisely aimed attacks that would quickly subdue victims. Alternatively, these giants could take to the air for aerial reconnaissance, soaring high above the landscape while searching for concentrations of potential prey. River valleys where herbivorous dinosaurs came to drink would have been particularly attractive hunting grounds, offering both abundant prey and the open terrain necessary for effective aerial approach. The social dynamics of these remarkable predators remained largely mysterious, But the anatomical evidence provided some tantalizing clues. The skull crests that adorned at least some species were clearly display structures, suggesting that visual communication played an important role in Azhdarchid behavior. The positioning and morphology of these crests indicated that they would have been most visible to other Azhdarchids when the animals were standing upright, perfect for territorial displays or species recognition signals. The coexistence of two Quetzalcoatlus species in the same environment suggested sophisticated behavioral mechanisms for avoiding direct competition. The size difference between the species would have naturally led to different prey preferences, but behavioral differences in hunting strategies, habitat preferences, or temporal activity patterns might have further reduced competitive interactions. The possibility of cooperative hunting behavior, while speculative, couldn't be ruled out entirely. The cognitive capabilities suggested by the brain case anatomy were certainly sufficient for complex behavioral strategies, and the advantages of coordinated hunting for such large predators would have been substantial. Imagine multiple Quetzalcoatlus working together to isolate and capture prey items that might be too dangerous or difficult for a single individual to handle safely. The reproductive biology of these giants remained one of the most mysterious aspects of their life history. The enormous size of adult animals raised fundamental questions about egg-laying behavior, nest construction, and parental care. How did creatures weighing hundreds of kilograms manage the delicate process of egg incubation without crushing their offspring? Where did they nest? And how did they protect their vulnerable young in environments teeming with other large predators? The growth patterns revealed by bone histology suggested that reaching full adult size was indeed a gradual process that took many years. This extended development period would have presented enormous challenges for survival, as juveniles would have been vulnerable to predation by both other Azhdarchids and the numerous large dinosaurian predators that shared their environment. The transformation from small, vulnerable hatchlings to towering adult predators would have required not just physical growth, but also the development of sophisticated hunting skills and behavioral strategies. Young Quetzalcoatlus would have needed to learn how to use their elongated necks effectively, how to coordinate the complex movements necessary for terrestrial locomotion, and how to master the challenging transition between ground-based and aerial locomotion. The environmental context in which these remarkable creatures lived was crucial to understanding their success as terrestrial giants. The late Cretaceous climate was significantly warmer than today's, supporting lush vegetation that could feed the enormous herds of herbivorous dinosaurs that formed the base of complex predatory ecosystems. Global sea levels were much higher, creating vast inland seas and extensive coastal plain environments that provided diverse habitat mosaics. The landscape of late Cretaceous North America was a patchwork of different environments, from fern-dominated prairies to gallery forests along river systems to extensive wetland complexes. This environmental diversity would have been perfect for versatile predators like Quetzalcoatlus, providing numerous different hunting opportunities and ensuring that food sources remained available even when individual habitats experienced temporary disruption. The seasonal patterns in this ancient world would have created dynamic hunting opportunities that changed throughout the year. Wet seasons might have concentrated prey around water sources, while dry periods could have forced herbivorous dinosaurs to undertake long-distance migrations in search of suitable feeding areas. For aerial predators with the mobility to track these movements, such environmental fluctuations would have been opportunities rather than challenges. The atmospheric composition during the late Cretaceous was also significantly different from today's, with higher oxygen levels and atmospheric pressure that would have aided the flight performance of large aerial animals. These conditions would have made powered flight easier for massive pterosaurs, helping to explain how creatures of such enormous size could achieve and maintain aerial locomotion. The extinction of Quetzalcoatlus and its relatives at the end of the Cretaceous represented one of the most profound losses in the history of vertebrate evolution. The asteroid impact that marked the end of the Mesozoic era didn't just eliminate the non-avian dinosaurs, it also ended one of the most successful experiments in aerial gigantism that evolution has ever produced. The ecological collapse that followed the impact event would have been particularly devastating for large predators like Azhdarshids. The disruption of food webs, the collapse of primary productivity, and the dramatic climate changes that characterized the immediate post-impact period would have eliminated the diverse prey base that these giants depended upon for survival. The loss of these remarkable creatures represented more than just another extinction event. It marked the end of an entire approach to aerial predation that has never been replicated. The ecological niche of giant flying predators remained empty after the Cretaceous extinction and has never been refilled by any subsequent evolutionary radiation. Yet the scientific legacy of Quetzalcoatlus continues to grow and evolve. Each new analytical technique, each technological advancement, each fresh perspective brings new insights into how these remarkable animals lived and functioned. The creature that began as a handful of mysterious bone fragments has become one of the most thoroughly understood pterosaurs. Yet it continues to surprise researchers with new revelations about its biology and behavior. The broader implications of Quetzalcoatlus research extend far beyond paleontology itself. These studies have contributed to our understanding of biomechanics, aerodynamics, and the fundamental constraints that govern the evolution of large flying animals. The engineering principles revealed by Azhdarshid anatomy continue to inspire aircraft designers and robotics engineers seeking to understand how to achieve efficient flight at large scales. The story of how our understanding of Quetzalcoatlus has evolved also serves as a powerful case study in the philosophy of science itself. The progression from speculation to hypothesis to rigorous testing and eventual understanding illustrates both the power and the limitations of scientific inquiry. Each phase of this intellectual journey built upon previous work, while occasionally requiring the complete abandonment of cherished theories in the face of contradictory evidence. The institutional obstacles that delayed progress for so many decades serve as a reminder of the crucial importance of open scientific communication and collaboration. The remarkable acceleration in discoveries that followed the release of detailed anatomical data demonstrates what becomes possible when artificial barriers to scientific progress are finally removed. As we look toward the future of Quetzalcoatlus research, the possibilities continue to expand. New fossils may yet be discovered that will further refine our understanding of these remarkable animals. Advanced analytical techniques will continue to extract additional information from existing specimens. And the integration of Azdarshid studies with broader research into Mesozoic ecosystems will undoubtedly reveal new insights into how these giants fit into their ancient world. The development of increasingly sophisticated computer models and virtual reality systems is opening new possibilities for understanding Azdarchid biology and behavior. Researchers can now create detailed simulations of how these animals moved, fed, and flew, testing hypotheses about their lifestyle in ways that would have been impossible just a few years ago. The story of Quetzalcoatlus northropi stands as one of the most remarkable tales in the annals of paleontological discovery. From mysterious fragments locked away in institutional vaults to one of the most completely understood pterosaurs known to science, this journey represents both the challenges and the triumphs that characterize our ongoing quest to understand the history of life on Earth. This magnificent creature, part terrestrial giant, part aerial marvel, part evolutionary experiment pushed to the very limits of biological possibility, continues to capture our imagination and challenge our understanding of what life can achieve. Named after an Aztec god, yet revealed through the most modern scientific techniques, Quetzalcoatlus bridges the gap between ancient mythology and contemporary knowledge, reminding us that reality can be far more extraordinary than any legend. The transformation in our understanding of this remarkable pterosaur over the past 5 decades serves as a powerful testament to the persistence of scientific curiosity and the eventual triumph of evidence over speculation. Each misconception that was corrected, each new discovery that refined our understanding, and each technological breakthrough that revealed previously hidden details contributed to the remarkable story of how science gradually assembled a coherent picture of one of the most extraordinary animals that ever lived. Today, when we envision Quetzalcoatlus stalking across the ancient landscapes of late Cretaceous North America, its giraffe-like proportions allowing it to tower above the vegetation, its keen eyes scanning for prey, its massive wings folded against its body like the cloak of some prehistoric titan. We're not just imagining another extinct animal. We're glimpsing a world where the very boundaries of biological possibility were pushed further than they have ever been pushed before or since. This is the legacy of Quetzalcoatlus northropi, not just as the largest flying animal that ever lived, but as a reminder that the history of life on Earth encompasses wonders that continue to exceed our wildest expectations. In understanding this magnificent creature, we don't just learn about pterosaur biology or Mesozoic ecosystems. We gain insight into the extraordinary creativity and endless possibility that characterize the evolutionary process itself. The journey from mystery to understanding that has defined Quetzalcoatlus research serves as a microcosm of scientific progress more broadly. It reminds us that knowledge is not static, but constantly evolving, that today's certainties may become tomorrow's misconceptions, and that the natural world will always retain the capacity to surprise and amaze us with revelations that challenge our most fundamental assumptions about what is possible in the realm of living things. As we stand at this pivotal moment in paleontological history, something truly extraordinary was beginning to unfold in laboratories and research institutions around the world. The detailed anatomical revelations of 2021 had unleashed a flood of new research possibilities that would have seemed like science fiction just a few years earlier. Scientists were no longer limited to educated guesses and fragmentary comparisons. They could finally examine the actual structural details that had made these remarkable creatures possible. The bone microstructure studies that became feasible with access to comprehensive specimens revealed architectural principles that pushed the boundaries of biological engineering. When researchers examined thin sections of Quetzalcoatlus wing bones under high-powered microscopes, they discovered internal frameworks that resembled the most advanced aerospace composites. The hollow spaces weren't simply empty cavities, but were filled with intricate networks of supporting struts and cross braces that provided maximum strength while minimizing weight. These structural revelations had profound implications for understanding how such massive flying animals could exist at all. The traditional models of scaling and flying creatures suggested that there should be upper limits to the size that powered flight could support. Yet here was clear evidence that evolution had found ways to circumvent these theoretical constraints through sophisticated architectural solutions that human engineers were only beginning to appreciate. The respiratory system adaptations revealed through detailed anatomical study were equally remarkable. The extensive pneumatization of the skeleton wasn't just about weight reduction. It was part of an integrated breathing system that would have allowed these giants to maintain the high metabolic rates necessary for powered flight despite their enormous size. The air sac networks that permeated their bones were connected to breathing passages that could move vast volumes of air through the body with each breath. This respiratory efficiency would have been absolutely crucial for animals that needed to switch rapidly between the different metabolic demands of terrestrial hunting and aerial locomotion. On the ground, stalking through fern prairies and scanning for prey, Quetzalcoatlus could have maintained a relatively relaxed breathing pattern. But when the moment came to launch into flight, their sophisticated respiratory system could instantly ramp up to support the enormous energy demands of getting hundreds of kilograms of animal airborne and keeping it there. The cardiovascular adaptations that would have been necessary to support such a lifestyle boggled the imagination. The heart of a giant Ashdarshid would have been a massive organ capable of pumping blood through an incredibly long neck to a brain positioned 6 meters above the ground when the animal was standing upright. The blood pressure requirements alone would have necessitated cardiovascular adaptations that had no parallels in the modern world. But perhaps most fascinating were the neurological adaptations that the detailed skull studies began to reveal. The brain case of Quetzalcoatlus was proportionally larger than in most other pterosaurs, suggesting cognitive capabilities that went far beyond simple predatory instincts. The regions associated with spatial processing and motor coordination were particularly well developed, perfect adaptations for an animal that needed to coordinate complex movements across an enormous body while transitioning between terrestrial and aerial locomotion. The visual processing centers were equally impressive, indicating that these creatures possessed exceptional eyesight that would have been crucial for their lifestyle as aerial terrestrial predators. From their elevated vantage point on the ground or while soaring high above the landscape, Quetzalcoatlus would have been able to spot potential prey at distances that would have been impossible for ground-bound predators to achieve. The integration of all these physiological systems created a predator of unprecedented capabilities. Imagine the hunting scenarios that would have been possible for such a versatile creature. A Quetzalcoatlus could spend the morning hours methodically working its way across miles of fern prairie, using its elevated position and exceptional vision to scan for movement that might betray the presence of prey. When something interesting was spotted, the long neck could extend forward for a closer look without the need to move the massive body and potentially alert the target. If the prey proved suitable and catchable, the strike would have been devastatingly effective. The neck could accelerate the massive beak to incredible speeds across remarkable distances, delivering attacks with enough force to subdue animals weighing hundreds of kilograms. But if the target proved too dangerous or simply escaped, the pterosaur could instantly switch to aerial mode, launching itself into the sky to continue hunting from an entirely different perspective. The versatility of this hunting system would have made Quetzalcoatlus incredibly effective in the dynamic environments of the late Cretaceous. Seasonal changes in prey distribution, temporary disruptions in local food webs, or the simple need to avoid dangerous encounters with other large predators could all be addressed through strategic use of flight capabilities. The social implications of such advanced cognitive and sensory capabilities remained tantalizingly mysterious. The brain anatomy suggested that these animals were capable of complex behaviors that might have included sophisticated communication systems, territorial displays, or even cooperative hunting strategies. The skull crests that adorned at least some species were clearly visual display structures, but how they were used in social contexts remained largely speculative. The possibility of complex social behaviors in these giants opened up entirely new dimensions for understanding late Cretaceous ecosystems. If Ajdarchids engaged in territorial disputes, mating displays, or cooperative hunting, their impact on their environment would have extended far beyond simple predator-prey relationships. They might have functioned as ecosystem engineers, influencing the distribution and behavior of numerous other species through their presence and activities. The mating behaviors of these remarkable creatures would have been spectacular affairs. Imagine the courtship displays of animals with 30-foot wingspans and 6-meter-tall necks. The aerial acrobatics alone would have been breathtaking, with potential mates demonstrating their flying prowess through elaborate maneuvers that showcased both their physical capabilities and their genetic fitness. The nesting requirements of such enormous animals presented fascinating challenges. Where could creatures of this size safely lay their eggs and incubate them without crushing the developing embryos? The nest sites would have needed to be large enough to accommodate animals, with the footprint of small buildings, yet secure enough to protect vulnerable eggs and young from the numerous predators that shared their environment. The parental care strategies that would have been necessary for raising young Quetzalcoatlus were equally intriguing. The extended development period suggested by bone histology meant that parents would have needed to protect and provision their offspring for many years. This would have required sophisticated behavioral adaptations and possibly even the establishment of family territories where young could develop safely. The growth trajectories of these giants represented one of the most remarkable transformations in the animal kingdom. Hatchlings that might have weighed only a few kilograms would eventually develop into predators weighing hundreds of times more. The intermediate stages of this development would have presented unique challenges, with juveniles needing to survive as both their size and their capabilities changed dramatically. Young Quetzalcoatlus would have occupied entirely different ecological niches at different stages of their development. Newly hatched individuals might have been small enough to hide in vegetation and feed on insects and small vertebrates. As they grew larger, they would have gradually transitioned to hunting bigger prey, while simultaneously developing the flight capabilities that would eventually make them masters of both terrestrial and aerial environments. The learning curve for developing the complex motor skills necessary for effective hunting would have been steep. Coordinating strikes with a neck that might be longer than the entire body of most modern animals required precision and timing that could only come through extensive practice. Young animals would have needed to master not just the mechanics of the strike itself, but also the complex behavioral strategies necessary to get close enough to pray for the strike to be effective. The transition from purely terrestrial juvenile behavior to the aerial terrestrial lifestyle of adults would have been a remarkable transformation. Learning to fly with wings that eventually spanned 30 feet would have required gradual development of the massive flight muscles and the sophisticated neuromuscular coordination necessary to control such enormous flight surfaces. The environmental pressures that shaped the evolution of these remarkable adaptations were as complex as the animals themselves. The late Cretaceous world was a place of extraordinary biological productivity and diversity, but it was also intensely competitive. The successful evolution of giant Ashdarchids represented a response to specific ecological opportunities that had never existed before and would never exist again. The abundance of large herbivorous dinosaurs created unprecedented opportunities for predators that could access prey items in the size range between what smaller predators could handle and what the largest dinosaurian predators typically targeted. Juvenile sauropods, hadrosaurs, and ceratopsians would have represented ideal prey for creatures with the size and capabilities of Quetzalcoatlus, large enough to provide substantial nutritional rewards, but not so large as to be impossible to subdue. The continental geography of the late Cretaceous also played a crucial role in Ashdarkid's success. The extensive inland areas created by high global sea levels provided vast territories where terrestrial predators with flight capabilities could operate effectively. These continental interiors were characterized by seasonal climates that created predictable patterns of resource availability, perfect conditions for mobile predators that could track these seasonal changes. The atmospheric conditions during this period were also ideal for supporting large flying animals. Higher atmospheric density and oxygen concentrations would have made powered flight easier for massive creatures, while the warm global climate would have provided abundant thermal currents that could be exploited for efficient soaring between hunting grounds. But even as we celebrate the remarkable success of these evolutionary giants, their ultimate fate serves as a sobering reminder of how quickly even the most successful adaptations can become liabilities when environmental conditions change rapidly. The asteroid impact that ended the Cretaceous period created environmental disruptions that were particularly devastating for large, specialized predators. The collapse of primary productivity that followed the impact would have eliminated the herbivore populations that formed the base of Ashdarkid food webs. The climate disruptions and habitat destruction would have made their flight capabilities irrelevant. There would have been nowhere to fly to escape the global environmental catastrophe. The extinction of Quetzalcoatlus and its relatives represented more than just the loss of impressive individual species. It marked the end of an entire evolutionary strategy that had taken millions of years to perfect. The ecological niche of giant aerial terrestrial predators has remained empty ever since, despite numerous opportunities for other animal groups to evolve into similar roles. This permanent vacancy in terrestrial ecosystems serves as a testament to how difficult it is to evolve the complex suite of adaptations necessary for aerial gigantism. The combination of structural, physiological, and behavioral innovations that made Ashdarkids possible represented such a specific evolutionary solution that it has never been replicated by any subsequent radiation of flying animals. The legacy of these remarkable creatures continues to influence scientific thinking across multiple disciplines. Engineers studying the structural properties of Ashdarkid bones have gained insights that are applicable to the design of lightweight yet strong materials for aerospace applications. The flight mechanics revealed by biomechanical studies of pterosaur locomotion continue to inform the development of more efficient aircraft designs. But perhaps most importantly, the study of Quetzalcoatlus has contributed to our fundamental understanding of evolutionary processes and the constraints that govern the evolution of complex organisms. These creatures pushed the boundaries of what was possible in flying animals further than any before or since, demonstrating that evolution is capable of solutions that exceed our most optimistic expectations about biological possibilities. The methodological advances that emerged from decades of Quetzalcoatlus research have also had lasting impacts on paleontological practice more broadly. The integration of biomechanical modeling, advanced imaging techniques, and comparative anatomical studies that characterize the most recent phase of Ajdarshid research has become a template for investigating other complex paleobiological questions. The institutional lessons learned from the long delay in publishing comprehensive descriptions of these remarkable fossils have also influenced how the scientific community approaches the stewardship of important paleontological resources. The recognition that scientific progress depends on open access to crucial specimens has led to new policies and practices that prioritize research access while still protecting valuable fossils from damage or loss. As new analytical techniques continue to emerge, the potential for additional discoveries about Quetzalcoatlus biology seems limitless. Molecular paleontology techniques that can extract chemical information from fossil bones may eventually reveal details about Ajdarshid physiology that are currently impossible to determine from morphological studies alone. Advanced computer modeling capabilities continue to open new possibilities for understanding how these remarkable animals functioned as integrated biological systems. Virtual reality reconstructions now allow researchers to explore Ajdarshid anatomy and behavior in ways that would have seemed like pure fantasy just a few years ago. The ongoing discovery of new Ajdarshid species from around the world continues to provide comparative context that enhances our understanding of Quetzalcoatlus specifically. Each new species reveals different solutions to the challenges of aerial gigantism, highlighting the remarkable diversity of approaches that evolution explored within this successful lineage. The integration of Quetzalcoatlus research with broader studies of late Cretaceous ecosystems continues to reveal new insights into how these predators fit into their ancient world. Climate modeling, vegetation reconstructions, and studies of contemporary fauna all contribute to an increasingly detailed picture of the environmental context in which these giants lived and thrived. But beyond all the scientific advances and technological innovations, perhaps the most enduring legacy of Quetzalcoatlus research lies in its capacity to inspire wonder and curiosity about the natural world. These magnificent creatures represent life pushed to its absolute limits. Evolution, exploring possibilities that seem to defy common sense, yet are grounded in solid biological reality. The story of how our understanding of these remarkable animals has evolved over the past 5 decades serves as a powerful reminder that science is not a collection of static facts, but an ongoing process of discovery and refinement. Each generation of researchers builds upon the work of their predecessors while bringing new tools, new perspectives, and new questions to bear on enduring mysteries. The transformation of Quetzalcoatlus from mysterious fragments to one of the most completely understood pterosaurs illustrates both the power and the patience required for effective scientific inquiry. Some questions can be answered quickly with the right techniques and sufficient resources, but others require decades of persistent effort and the gradual accumulation of evidence from multiple sources. The institutional obstacles that delayed progress for so long serve as cautionary examples of how scientific advancement can be hindered by artificial barriers to collaboration and communication. But they also demonstrate the resilience of scientific curiosity and the eventual triumph of evidence-based inquiry over institutional inertia. As we look toward the future of pterosaur research more broadly, the Quetzalcoatlus studies serve as both an inspiration and a template for tackling other complex paleobiological questions. The integration of multiple analytical approaches, the emphasis on biomechanical testing of functional hypotheses, and the commitment to comprehensive anatomical description that characterize the most successful phases of this research program provide a roadmap for investigating other remarkable extinct creatures. The technological capabilities that will be available to future researchers promise even more dramatic advances in our understanding of these ancient giants. Artificial intelligence applications that can extract patterns from complex anatomical data, quantum computing approaches to biomechanical modeling, and molecular techniques that can reveal chemical signatures preserved in fossil bones will all contribute to an increasingly sophisticated understanding of how these remarkable animals lived and functioned. But regardless of what new technologies and analytical approaches become available, the fundamental questions that drive paleontological inquiry will remain the same. How did these remarkable creatures live? What drove their evolution? How did they interact with their environment and with each other? What can they teach us about the possibilities and constraints that govern life on Earth? The answers to these questions, as revealed through decades of patient scientific investigation of Quetzalcoatlus and its relatives, remind us that the history of life on Earth encompasses wonders that far exceed anything in our contemporary experience. These magnificent flying giants, stalking across ancient landscapes with the majesty of mythological creatures, yet grounded in solid biological reality, represent just one example of the extraordinary creativity and endless possibility that characterize the evolutionary process. In understanding Quetzalcoatlus, we gain more than just knowledge about pterosaur biology or Mesozoic ecosystems. We gain insight into our own place in the grand sweep of evolutionary history, our role as the current inheritors of a planet that has supported an almost unimaginable diversity of remarkable creatures across billions of years of biological innovation. The story of these magnificent pterosaurs serves as a bridge connecting the mythological imagination of ancient cultures, which created gods with the power of flight, to the scientific reality of creatures that actually possess such capabilities. In studying Quetzalcoatlus, we discover that reality can indeed exceed the wildest flights of imagination, that the natural world contains wonders that challenge our most fundamental assumptions about what is possible in the realm of living things. This is perhaps the most profound legacy of Quetzalcoatlus research, the recognition that we inhabit a universe where evolution has explored possibilities that push the very boundaries of physical and biological constraints. These remarkable creatures remind us that the capacity for wonder and discovery that drives scientific inquiry is not just an academic exercise, but a fundamental aspect of what makes us human. The transformation in our understanding of Quetzalcoatlus over the past 5 decades represents more than just another success story in paleontological research. It serves as a testament to the power of persistent scientific curiosity, the importance of technological innovation in advancing knowledge, and the crucial role that institutional cooperation plays in facilitating scientific progress. As we continue to explore the mysteries of these ancient giants, we are not just learning about the past, we are gaining insights that inform our understanding of biological possibilities more broadly. The engineering principles revealed by Astarchid anatomy, the ecological strategies employed by these versatile predators, and the evolutionary innovations that made aerial gigantism possible all contribute to our broader understanding of how complex biological systems function and evolve. The story of Quetzalcoatlus northropi, from enigmatic fragments to sophisticated predator, stands as one of the most remarkable tales of scientific discovery in the modern era. It demonstrates that even the most famous fossils can continue to surprise us, that scientific understanding is always provisional and subject to revision, and that the natural world will always retain the capacity to exceed our expectations about what life can achieve. These magnificent creatures, named after ancient gods yet revealed through the most modern scientific techniques, serve as eternal reminders that we live in a universe where the impossible can become possible, where the boundaries of biological potential are constantly being redefined, and where the patient application of scientific inquiry can unlock secrets that have been hidden for millions of years. The legacy of Quetzalcoatlus extends far beyond the confines of paleontology itself, touching on fundamental questions about the nature of scientific progress, the relationship between technology and discovery, and our own place in the vast tapestry of evolutionary history. In understanding these remarkable creatures, we gain not just knowledge about the past, but wisdom about the endless possibilities that the future may hold. As researchers dove deeper into the treasure trove of anatomical data that had finally been unlocked, something remarkable began to emerge that would challenge even the most recent reconstructions. The feeding mechanics that scientists had envisioned based on comparative studies with modern animals proved to be far more sophisticated than anyone had anticipated. When biomechanical engineers created detailed computer models of the skull and neck apparatus, they discovered that Quetzalcoatlus possessed striking capabilities that had no equivalent in the contemporary world. The precision with which these giants could manipulate their enormous beaks was absolutely staggering. The neck vertebrae showed evidence of muscle attachment sites that would have allowed incredibly fine motor control despite the massive scale of the apparatus. Think about the challenge this represented, coordinating precise movements across a neck that stretched longer than a modern giraffe's entire body, while supporting a skull that could accommodate objects the size of refrigerators within its beak. Yet, the anatomical evidence suggested that Quetzalcoatlus could strike with surgical precision when targeting smaller prey, then immediately switch to delivering devastating attacks capable of subduing much larger animals. This versatility in feeding behavior would have been crucial for survival in the competitive ecosystems of the late Cretaceous, where successful predators needed to be opportunistic and adaptable. The hunting scenarios that emerged from these biomechanical studies painted pictures of predatory behavior that seemed almost impossible to believe. A single Quetzalcoatlus could have systematically worked through entire herds of small dinosaurs, picking off individuals with lightning-fast strikes while the rest of the group remained unaware of the danger towering above them. The elevated hunting platform provided by their giraffe-like proportions would have given them visual advantages that no ground-based predator could match. But perhaps most intriguingly, the refined anatomical studies revealed evidence for feeding behaviors that went beyond simple predation. The beak structure showed adaptations that would have been perfect for scavenging, suggesting that these giants might have functioned as both active hunters and opportunistic scavengers depending on circumstances and prey availability. The scavenging capabilities would have been particularly valuable during seasonal periods when active prey became scarce or environmental conditions made hunting more challenging. A Quetzalcoatlus could have switched from aggressive predation to patient scavenging, using its flight abilities to locate carcasses across vast territories, while its powerful beak allowed it to access nutritious internal organs that smaller scavengers couldn't reach. This behavioral flexibility represented yet another dimension of the remarkable adaptability that characterized these evolutionary giants. Rather than being locked into a single feeding strategy, they possessed the anatomical and presumably behavioral tools necessary to exploit whatever feeding opportunities their environment provided. The social implications of such advanced feeding capabilities became even more fascinating when researchers considered the possibility of competitive interactions between different Azhdarchid species. The coexistence of multiple large pterosaur species in the same environment would have required sophisticated behavioral mechanisms to avoid direct competition for limited food resources. The size differences between Quetzalcoatlus northropi and its smaller relative Lawsoni would have naturally led to different prey preferences, but the behavioral strategies they employed might have been even more important for avoiding competitive conflicts. Different hunting times, preferred habitat types, or specialized feeding techniques could have allowed these closely related giants to share the same landscape without directly competing for the same resources. The territorial behaviors that might have governed interactions between these massive predators boggled the imagination. Animals with 30-foot wingspans defending territories would have created one of the most spectacular displays of dominance behavior in the history of terrestrial ecosystems. The aerial confrontations alone would have been breathtaking, with rival males engaging in aerial combat that dwarfed anything seen in modern flying animals. The wing loading calculations that became possible with detailed anatomical measurements revealed flight capabilities that exceeded even the most optimistic earlier estimates. These creatures weren't just capable of powered flight. They were remarkably efficient flyers that could maintain aerial locomotion with energy expenditures that were actually quite reasonable for their enormous size. The flight endurance that this efficiency would have provided opened up entirely new possibilities for understanding Azhdarchid ecology and behavior. Rather than being limited to short-distance flights between feeding areas, these giants might have been capable of true long-distance migration, following seasonal changes in prey availability across continental distances. Imagine flocks of Quetzalcoatlus undertaking migrations that spanned thousands of kilometers, moving between different regions as environmental conditions changed throughout the year. The logistical challenges of such migrations would have been enormous, requiring sophisticated navigation abilities and the capacity to locate suitable feeding areas in unfamiliar territories. But the rewards of such mobility would have been equally substantial. Predators that could track seasonal abundances of prey across continental scales would have enjoyed advantages that no purely terrestrial predator could match. Drought conditions in one region could be escaped by flying to areas experiencing more favorable environmental conditions. The navigation capabilities that would have been necessary for such long-distance movements were supported by anatomical evidence for sophisticated sensory systems. The inner ear structures showed adaptations for maintaining orientation during flight, while the brain anatomy suggested cognitive capabilities sufficient for complex spatial processing and memory formation. These neurological adaptations raise fascinating questions about Ajdarsheet intelligence and behavioral complexity. The brain-to-body ratios suggested cognitive capabilities that approached or exceeded those of modern birds, implying behavioral sophistication that might have included complex social interactions, learning abilities, and problem-solving skills. The learning capabilities that such intelligence would have supported were particularly intriguing when considered in the context of the extended development periods that characterized these giants. Young Quetzalcoatlus would have had years to develop not just their physical capabilities, but also the complex behavioral repertoires necessary for successful survival as adults. The cultural transmission of hunting techniques, territorial boundaries, migration routes, and social behaviors might have played crucial roles in Ajdarsheet society. Experienced adults could have taught younger individuals the sophisticated skills necessary for effective predation, efficient flight, and successful social interaction. This possibility of cultural learning added yet another layer of complexity to late Cretaceous ecosystems. If Ajdarchids possessed the cognitive capabilities for cultural transmission, their impact on their environment would have extended far beyond simple predator-prey relationships. They might have functioned as ecosystem engineers whose learned behaviors influenced the distribution and evolution of numerous other species. The prey species that coexisted with these remarkable predators would have faced selective pressures unlike anything in the modern world. The combination of aerial reconnaissance capabilities and terrestrial stalking abilities would have made traditional anti-predator strategies largely ineffective against Ajdarsheet attacks. Herbivorous dinosaurs living in environments dominated by giant Ajdarchids would have needed to develop entirely new defensive strategies. Herd behaviors, vigilance patterns, and habitat selection would all have been influenced by the presence of predators that could attack from above, approach undetected across great distances, and deliver devastating strikes from elevated positions. The evolutionary arms race between Ajdarchid predators and their potential prey would have driven innovations in both attack and defense strategies that pushed the boundaries of what was possible in predator-prey interactions. This co-evolutionary dynamic would have been a major force shaping the evolution of late Cretaceous terrestrial ecosystems. The habitat modifications that might have resulted from Ozdarkid hunting pressure were equally fascinating to consider. Prey species might have been forced to concentrate around areas that provided protection from aerial attack, creating unusual patterns of herbivore distribution that would have influenced vegetation dynamics across entire landscapes. The trampling effects, selective browsing patterns, and nutrient redistribution that resulted from these modified herbivore behaviors would have cascaded through entire ecosystems, influencing plant communities, soil development, and water cycling patterns. In this way, the presence of giant Ozdarkids might have shaped the very structure of the landscapes they inhabited. The seasonal movements of these remarkable predators would have created additional layers of ecological complexity. Areas that provided suitable nesting sites might have experienced intense predation pressure during breeding seasons, while regions along migration routes would have been subject to periodic visitations by enormous numbers of giant pterosaurs. The environmental impacts of such large-scale movements would have been substantial. The temporary concentration of hundreds or thousands of giant predators in specific areas would have created intense competition for local resources, potentially leading to significant modifications of local prey populations and habitat structure. But even as researchers celebrated these remarkable insights into Ozdarkid biology and ecology, nagging questions remained about the ultimate factors that had driven the evolution of such extreme adaptations. Why did aerial gigantism evolve during the late Cretaceous when it had never appeared before and would never appear again? The answer seemed to lie in the unique environmental conditions that characterized the final phase of the Mesozoic era. The combination of warm global climates, high atmospheric density, abundant prey resources, and extensive continental landscapes created a perfect storm of conditions that favored the evolution of giant aerial predators. The warm global temperatures would have supported the high metabolic rates necessary for powered flight in such massive animals, while the dense atmosphere would have made flight mechanically easier. The abundance of large herbivorous dinosaurs provided prey resources that could support predators of unprecedented size, while the extensive continental interiors provided the vast territories necessary for such large predators to find sufficient food. But this perfect combination of favorable conditions was inherently unstable. The same geological and climatic processes that had created ideal conditions for Ozdarkid evolution were also driving toward the environmental catastrophe that would ultimately destroy their world. The late Cretaceous was a time of intense geological activity, with massive volcanic eruptions, changing sea levels, and shifting continental configurations, creating environmental instability that would have challenged even the most adaptable species. The Ozdarkids that had evolved to exploit the opportunities provided by this dynamic world were also vulnerable to its periodic disruptions. The asteroid impact that ended the Cretaceous represented just the final blow to ecosystems that were already under stress from volcanic activity and climate change. The collapse of primary productivity that followed the impact eliminated the herbivore populations that supported Ashtarshid food webs, while the dramatic environmental changes made their sophisticated adaptations irrelevant. The extinction of these remarkable creatures marked not just the end of individual species, but the permanent closure of an evolutionary pathway that had required millions of years to develop. The specific combination of anatomical, physiological, and behavioral adaptations that made aerial gigantism possible was so complex and specialized that it has never been replicated by any subsequent evolutionary radiation. This evolutionary uniqueness makes the scientific study of Ashtarchids particularly valuable for understanding the broader principles that govern biological innovation. These creatures represent evolution pushed to its absolute limits, demonstrating possibilities that stretch our understanding of what life can achieve while remaining grounded in fundamental physical and biological constraints. The engineering principles revealed by Ashtarshid anatomy continue to inspire technological innovations in fields ranging from aerospace design to material science. The structural solutions that evolution discovered for achieving aerial gigantism provide templates for human engineers seeking to develop more efficient aircraft and lightweight yet strong materials. But perhaps most importantly, the study of these remarkable creatures serves as a powerful reminder of the incredible creativity and endless possibility that characterize the evolutionary process. In a universe where giant flying reptiles once stalked across ancient landscapes with the majesty of living myths, we are reminded that reality can indeed exceed our wildest imagination. The transformation in our understanding of Quetzalcoatlus over the past 5 decades represents more than just another success story in paleontological research. It illustrates the fundamental nature of scientific progress itself, the gradual accumulation of evidence, the testing and refinement of hypotheses, and the occasional paradigm shifts that completely transform our understanding of natural phenomena. Each phase of this remarkable scientific journey built upon previous work, while occasionally requiring the complete abandonment of cherished theories in the face of contradictory evidence. The progression from mysterious fragments to sophisticated predator demonstrates both the power and the patience required for effective scientific inquiry into the deep past. The institutional lessons learned from the decades-long delay in publishing comprehensive descriptions have influenced how the scientific community approaches the stewardship of important paleontological resources. The recognition that scientific progress depends on open access to crucial specimens has prioritized research while protecting valuable to emerge. The potential led to new policies that analytical techniques continue fossils. As new for additional discoveries about Ashtarshid biology seems boundless, advances in molecular paleontology, computer modeling, and imaging technology promise to reveal details about these ancient giants that are currently impossible to determine from morphological studies alone. The ongoing discovery of new Ashtarchid species from around the world continues to provide comparative context that enhances our understanding of the entire gigantism, highlighting family. Each new species reveals different solutions to the challenges of the remarkable diversity of approaches that evolution explored within this successful lineage. But beyond all the technological advances and scientific discoveries, perhaps the most enduring legacy of Quetzalcoatlus research lies in its capacity to inspire wonder about the natural world. These magnificent creatures remind us that we inhabit a universe where evolution has explored possibilities that challenge our most fundamental assumptions about biological potential. The story of how our understanding of these remarkable animals has evolved serves as a testament to human curiosity and the power of scientific inquiry to unlock secrets that have been hidden for millions of years. In studying Quetzalcoatlus, we gain not just knowledge about ancient life, but wisdom about the endless possibilities that biological innovation can achieve. These extraordinary pterosaurs, bridging the gap between scientific reality and mythological imagination, stand as eternal reminders that the history of life on Earth encompasses wonders that far exceed anything in our contemporary experience. They represent just one example of the remarkable creativity that has characterized billions of years of evolutionary experimentation on our planet. In understanding the magnificent giants that once ruled both terrestrial and aerial domains, we discover that the boundaries of what we consider possible in the natural world are constantly being redefined by the patient application of scientific investigation. The creatures that seemed impossible when first discovered have been revealed as masterpieces of biological engineering that pushed the very limits of what life could achieve. The legacy of Quetzalcoatlus northropi extends far beyond paleontology itself, touching on fundamental questions about scientific progress, technological innovation, and our place in the vast sweep of evolutionary history. These remarkable animals serve as bridges connecting ancient worlds to modern understanding, mythology to scientific reality, and human imagination to the boundless creativity of the evolutionary process itself. The anatomical revelations that emerged from this unprecedented picture of these ancient predators. When scientists' access to detailed specimens began to paint an even more extraordinary, finely examined the joint mechanics that governed outstashid locomotion, they discovered engineering solutions that seemed to defy conventional understanding of how such massive animals could function effectively on the ground. The hip and shoulder joints showed modifications that were unlike anything seen in other pterosaurs or indeed in any other flying animals. These weren't just scaled-up versions of smaller pterosaur anatomy. They represented fundamental redesigns of the basic pterosaur body plan to accommodate the unique challenges of terrestrial gigantism combined with flight capability. The pelvic girdle, in particular, revealed adaptations that would have been crucial for supporting the enormous weight of these creatures during terrestrial locomotion. The bone structure showed reinforcement patterns that distributed loading forces in ways that maximized strength while maintaining the flexibility necessary for the complex movements involved in launching into flight. But it was the forelimb anatomy that proved most revolutionary in terms of understanding as their chid capabilities. The wing bones weren't just flight structures. They were sophisticated multi-purpose limbs that could function equally well as terrestrial supports, flight surfaces, and even manipulative appendages when the situation demanded. The wrist joints showed evidence of remarkable flexibility that would have allowed these animals to adjust their wing configuration for different activities. During terrestrial locomotion, the wings could be folded and positioned to provide stable quadrupedal support. When preparing for flight, the same joints could rapidly reconfigure the wing geometry for optimal aerodynamic efficiency. This mechanical versatility extended to the wing fingers themselves, which showed adaptations that went far beyond simple flight membrane support. The robust construction and specialized joint surfaces suggested that these enormous digits could have been used for manipulating objects, clearing obstacles, or even assisting in prey capture when circumstances required. The implications of such multifunctional anatomy were staggering. These weren't just flying animals that happened to walk occasionally. They were sophisticated predators that had evolved integrated solutions to the challenges of operating effectively in multiple domains. Every anatomical system was designed to support both terrestrial and aerial activities with remarkable efficiency. The muscle attachment sites revealed throughout the skeleton told the story of creatures with almost unimaginable physical capabilities. The flight muscles alone would have been massive organs capable of generating the enormous forces necessary to lift hundreds of kilograms of animal into the air from a standing start. But equally impressive were the terrestrial locomotion muscles that provided the strength and coordination necessary for effective ground-based movement. The neck musculature deserves special attention for its sheer complexity and power. The cervical vertebrae showed attachment sites for dozens of different muscle groups that would have provided incredibly precise control over head and neck positioning. This muscular system could generate lightning-fast strikes across remarkable distances while maintaining the strength necessary to subdue struggling prey. The feeding apparatus that emerged from these detailed anatomical studies was revealed to be far more sophisticated than even the most optimistic earlier reconstructions had suggested. The beak wasn't just a simple grabbing tool, it was a precision instrument capable of delivering attacks that could be adjusted for prey items ranging from tiny mammals to juvenile dinosaurs weighing several tons. The jaw mechanics showed adaptations for both crushing and piercing, allowing these predators to adjust their attack strategy depending on the type of prey encountered. Small, soft-bodied animals could be dispatched with gentle precision, while larger, more robust prey could be subjected to devastating, crushing forces that would quickly end any struggle. But perhaps most remarkably, the anatomical evidence suggested that these giants possessed sensory capabilities that would have made them incredibly effective hunters despite their enormous size. The skull showed enlarged areas for processing visual information, indicating eyesight that would have been exceptional even by the standards of modern birds of prey. The inner ear structures revealed adaptations for maintaining balance and spatial orientation that would have been crucial for animals transitioning between terrestrial stalking and aerial flight. These vestibular systems could process information about body position and movement with the precision necessary to coordinate complex behaviors across an enormous body. The olfactory regions of the skull suggested that scent detection played an important role in Ajdarchid behavior, possibly for locating carrion across vast distances or tracking potential prey through complex terrain. The combination of exceptional vision and sophisticated chemical detection would have made these predators incredibly efficient at locating feeding opportunities. When researchers began modeling the hunting behaviors that would have been possible with such advanced sensory and locomotor capabilities, the scenarios that emerged challenged every preconception about how large predators operate in natural ecosystems. A single Quetzalcoatlus could have systematically hunted across territories spanning hundreds of square kilometers, using flight to move between hunting grounds and terrestrial stalking to capture prey. The energy efficiency of this hunting strategy would have been remarkable. Rather than expending enormous amounts of energy in continuous flight like modern seabirds, these giants could conserve energy through efficient ground-based hunting, punctuated by strategic flights to new areas when local prey became scarce or wary. The seasonal hunting patterns that would have resulted from such mobility boggled the imagination. During periods when prey was abundant and predictably distributed, Quetzalcoatlus could have established temporary territories and hunted systematically on foot. When environmental conditions changed or prey became scarce, they could simply take to the skies and relocate to more favorable hunting grounds. This behavioral flexibility would have been particularly valuable in the dynamic environments of the late Cretaceous, where seasonal climate variations created constantly shifting patterns of resource availability. Predators that could track these changes would have enjoyed enormous advantages over competitors limited to single locations or habitats. The social dynamics that might have governed interactions between these mobile giants remained tantalizingly mysterious, but the anatomical evidence provided intriguing clues. The skull crests that adorned at least some species were clearly visual display structures, suggesting that communication and recognition played important roles in Ajdarchid behavior. The size and positioning of these crests indicated that they would have been most visible when the animals were standing upright at full height, perfect for long-distance signaling between individuals across the vast landscapes they inhabited. The display behaviors that might have involved such structures would have been spectacular affairs. With giants using their imposing stature and elaborate head ornaments to communicate territorial claims, mating intentions, or species identity. The possibility of complex social hierarchies among these remarkable predators opened entirely new dimensions for understanding late Cretaceous ecosystems. If Ajdarchids engaged in sophisticated social behaviors, their impact on their environment would have extended far beyond simple predation to include territorial exclusion, resource monopolization, and possibly even cooperative hunting strategies. The cooperative hunting scenarios that might have been possible with such intelligent and mobile predators were particularly fascinating to contemplate. Groups of Quetzalcoatlus working together could have tackled prey items that would have been impossible for individual hunters to subdue safely. Coordinated attacks on large herbivorous dinosaurs might have allowed these predators to access food resources that were otherwise beyond their reach. The logistical challenges of organizing such cooperative hunts would have been enormous, requiring sophisticated communication systems and the ability to coordinate complex behaviors across multiple individuals. But the anatomical evidence for advanced cognitive capabilities suggested that Azhdarchids might have possessed the intellectual resources necessary for such behavioral complexity. The territorial behaviors that would have been necessary to support populations of such enormous predators would have created some of the most dramatic dominance displays in the history of terrestrial ecosystems. Animals with 30-foot wingspans engaging in aerial confrontations would have been breathtaking spectacles that dwarfed anything seen in modern flying animals. The energy costs of maintaining territories large enough to support giant predators would have been substantial, requiring efficient patrol strategies and the ability to quickly respond to territorial intrusions. The flight capabilities that made long-distance hunting possible would have been equally valuable for territorial defense and maintenance. The breeding behaviors of these remarkable creatures remained largely mysterious, but the anatomical evidence provided some tantalizing hints about what might have been involved. The robust construction of the pelvic region suggested that egg-laying would have required specialized behaviors to avoid damaging the developing embryos with the enormous weight of the parent. The nesting sites that would have been suitable for such massive animals presented fascinating logistical challenges. The nests would have needed to be large enough to accommodate creatures with the footprint of small buildings, yet constructed in locations that provided protection from other large predators and environmental hazards. The parental care strategies that would have been necessary for successfully raising young Azhdarchids were equally intriguing. The extended development period suggested by bone histology meant that parents would have needed to protect and provision their offspring for many years, while the juveniles gradually developed the size and capabilities necessary for independent survival. The growth trajectories that characterized Azhdarchid development represented one of the most remarkable transformations in the vertebrate world. Hatchlings that might have weighed only a few kilograms would eventually develop into predators weighing hundreds of times more, requiring dramatic changes not just in size, but in behavior, diet, and ecological role. The intermediate stages of this development would have presented unique challenges and opportunities. Young Azhdarchids would have occupied entirely different ecological niches at different points in their growth, gradually transitioning from small, vulnerable prey items to increasingly formidable predators in their own right. The learning processes that would have been necessary for developing the complex motor skills required for effective hunting would have been extensive, coordinating precise strikes with a neck that eventually stretched longer than most modern animals' entire bodies required practice and refinement that could only come through years of experience. The flight training that young Ashtarchids would have undergone represented another remarkable aspect of their development. Learning to control wings that eventually spanned 30 feet would have required gradual development of the massive flight muscles and the sophisticated neuromuscular coordination necessary to manage such enormous flight surfaces. The environmental context in which these remarkable developmental processes occurred was crucial for understanding how such complex life cycles could succeed in competitive ecosystems. The late Cretaceous world provided abundant resources and diverse habitats that could support the extended juvenile phases necessary for Ashtarchid development. But this same environmental richness also created intense competitive pressures that would have challenged every aspect of Ashtarchid survival strategies. The successful evolution of these giants represented a remarkable balance between exploiting available opportunities and managing the risks inherent in their enormous size and complex lifestyle. The predator-prey relationships that governed Ashtarchid ecology were unlike anything in the modern world. These creatures occupied positions at the very top of terrestrial food webs, while simultaneously serving as mobile links between different habitats and ecosystems through their flight capabilities. The cascading effects of Ashtarchid predation on prey populations would have influenced vegetation patterns, nutrient cycling, and habitat structure across vast landscapes. Their role as ecosystem engineers would have been particularly pronounced in areas where they concentrated for breeding or where seasonal hunting patterns created predictable predation pressure. The evolutionary arms race between these remarkable predators and their potential prey drove innovations in both attack and defense strategies that pushed the boundaries of what was possible in predator-prey interactions. Herbivorous dinosaurs living under the shadow of giant aerial predators would have faced selective pressures that shaped everything from herd behavior to habitat selection. The defensive strategies that evolved in response to Ashtarchid predation pressure would have included modifications to vigilance patterns, group coordination, and escape behaviors that had no parallels in ecosystems dominated by purely terrestrial predators. The ability to attack from above, approach undetected across great distances, and deliver devastating strikes from elevated positions would have made traditional anti-predator strategies largely ineffective. The habitat modifications that resulted from these predator-prey dynamics would have created landscape-scale patterns that influenced the distribution and evolution of numerous other species. Areas that provided protection from aerial attack might have become concentration points for herbivore populations, creating unusual vegetation patterns and soil nutrient distributions. The seasonal movements of Ashtarchid populations would have created additional layers of ecological complexity, with periodic concentrations of giant predators creating intense but temporary impacts on local ecosystems. The environmental effects of such large-scale movements would have cascaded through entire food webs, influencing everything from plant reproduction to small mammal population dynamics. As researchers continued to explore the implications of these remarkable discoveries, it became increasingly clear that Ashtarchids represented far more than just impressive individual species. They were keystone components of late Cretaceous terrestrial ecosystems, whose influence extended far beyond their direct predatory impacts. The global distribution of giant asdarshids during the final years of the Mesozoic suggested that this evolutionary strategy had been remarkably successful across a wide range of environmental conditions. Each continent developed its own distinctive asdarshid fauna, but all shared the fundamental adaptations that made aerial gigantism possible in terrestrial predators. The evolutionary origins of this remarkable lineage remained partially mysterious, but the anatomical evidence suggested that the transition to terrestrial gigantism had required numerous coordinated changes in skeletal architecture, muscle systems, and sensory capabilities. The complexity of these integrated adaptations helped explain why aerial gigantism had evolved so rarely in the history of life. The biomechanical constraints that governed asdarchid evolution also provided insights into why such creatures have never evolved again despite numerous opportunities for other animal groups to exploit similar ecological niches. The specific combination of anatomical innovations necessary for effective aerial terrestrial gigantism was so complex and specialized that it represented a unique evolutionary achievement. The technological applications that have emerged from studying asdarchid anatomy continue to influence engineering design across multiple fields. The structural principles revealed by pterosaur bone architecture have informed the development of lightweight yet strong materials, while the flight mechanics discovered through biomechanical modeling have contributed to more efficient aircraft designs. But perhaps most significantly, the study of these remarkable creatures has expanded our fundamental understanding of evolutionary possibilities and the constraints that govern biological innovation. In pushing the boundaries of what was possible in flying animals, asdarshids demonstrated that evolution is capable of solutions that exceed our most optimistic expectations about biological potential. The extinction of these magnificent creatures at the end of the Cretaceous represented more than just another casualty of mass extinction. It marked the permanent closure of an evolutionary pathway that had required millions of years to develop and has never been reopened despite changing environmental conditions that might have favored similar adaptations. This evolutionary uniqueness makes asdarchids particularly valuable for understanding the broader principles that govern biological innovation and the role that historical contingency plays in shaping the trajectory of life on Earth. These creatures remind us that evolution is not just about adaptation to current conditions, but also about the historical sequence of changes that make certain innovations possible while foreclosing others. The scientific legacy of asdarchid research extends far beyond the specific discoveries about these remarkable animals. The methodological approaches developed for studying fragmentary remains, the integration of multiple analytical techniques, and the emphasis on biomechanical testing of functional hypotheses have become templates for investigating other complex paleobiological questions. The institutional lessons learned from the prolonged delay in publishing comprehensive descriptions have influenced how the scientific community approaches the stewardship of important paleontological resources. The recognition That scientific progress depends on collaborative access to crucial specimens has led to new policies that balance research needs with conservation requirements. As new analytical techniques continue to emerge, the potential for additional discoveries about Azhdarchid biology and ecology seems unlimited. Advances in imaging technology, computer modeling, and chemical analysis promise to reveal details about these ancient giants that are currently impossible to determine from morphological studies alone. The story of how our understanding of these remarkable creatures has evolved over the past several decades serves as a powerful illustration of how scientific knowledge develops through the gradual accumulation of evidence, the testing and refinement of hypotheses, and the occasional paradigm shifts that completely transform our perspective on natural phenomena. Each phase of this scientific journey has built upon previous work, while sometimes requiring the complete abandonment of cherished theories in the face of new evidence. The transformation from mysterious fragments to sophisticated aerial predators demonstrates both the power and the patience required for effective scientific investigation of the deep past. The remarkable creatures that emerge from this scientific odyssey challenge our most fundamental assumptions about biological possibilities while remaining grounded in solid physical and evolutionary principles. These giants remind us that the history of life on Earth encompasses wonders that far exceed anything in our contemporary experience, serving as eternal testaments to the boundless creativity of evolutionary processes. In understanding Quetzalcoatlus and its remarkable relatives, we gain more than just knowledge about ancient ecosystems or pterosaur biology. We acquire insights into our own place in the grand sweep of evolutionary history and our role as current stewards of a planet that has supported an almost unimaginable diversity of extraordinary creatures across billions of years of biological innovation. The magnificent pterosaurs that once dominated late Cretaceous skies serve as bridges connecting mythological imagination to scientific reality, ancient worlds to modern understanding, and human curiosity to the endless possibilities that characterize life in our remarkable universe. Their story continues to unfold as new discoveries reveal ever more spectacular details about these masters of both terrestrial and aerial domains. The global reach of Azhdarchid's success became even more apparent as researchers began connecting discoveries from different continents into a coherent picture of worldwide dominance. These weren't isolated evolutionary experiments confined to specific regions. They represented a coordinated biological revolution that had swept across the planet during the twilight years of the dinosaur age. The Romanian discoveries revealed Azhdarchids that had adapted to European coastal environments, while specimens from Jordan showed how these giants had colonized even the arid margins of ancient Tethyan seaways. Each new find demonstrated variations on the basic Azhdarchid theme, modifications that allowed these remarkable predators to exploit local environmental conditions while maintaining the fundamental anatomical innovations that made their lifestyle possible. But it was the African discoveries that proved most intriguing for understanding the full scope of Azhdarchid diversity. The fragmentary remains suggested creatures that had pushed the boundaries of aerial gigantism even further than their North American relatives. These potential supergiants challenged existing ideas about the upper limits of vertebrate flight capability and raised tantalizing questions about what other remarkable species might yet be discovered. The anatomical variations revealed across this global distribution painted a picture of evolutionary experimentation on a continental scale. Different lineages had explored slightly different solutions to the challenges of aerial terrestrial predation, resulting in a remarkable diversity of approaches within the same basic body plan. Some species developed more robust skulls, suited for tackling larger prey, while others refined their flight capabilities for enhanced long-distance mobility. The climate modeling that accompanied these paleontological discoveries revealed environmental conditions that seemed almost designed to favor the success of giant flying predators. The late Cretaceous world was characterized by greenhouse conditions that created extensive thermal updrafts, perfect for soaring, while the elevated atmospheric density would have made powered flight mechanically easier for massive animals. The continental configurations during this period also played a crucial role in Azhdarchid's success. The extensive land masses created by high global sea levels provided vast territories where terrestrial hunting could be profitable, while the relatively short distances between continents would have allowed for occasional long-distance dispersal events that helped maintain genetic connectivity between regional populations. The seasonal patterns that characterized late Cretaceous climates created dynamic hunting opportunities that would have been ideal for mobile predators. Wet and dry cycles concentrated prey animals around reliable water sources during certain times of year, creating predictable hunting opportunities that flight-capable predators could exploit more effectively than their ground-bound competitors. The vegetation patterns that developed under these climatic conditions also influenced Azhdarchid hunting success. The open woodland and fern prairie environments that characterized much of the late Cretaceous landscape provided excellent visibility for aerial reconnaissance, while maintaining sufficient prey diversity to support large predators throughout the year. But even as researchers celebrated these insights into Azhdarchid global success, the shadow of extinction loomed large over every discovery. The very environmental conditions that had enabled these creatures to achieve such remarkable evolutionary success were also inherently unstable, driven by geological processes that were building toward the catastrophic conclusion of the Mesozoic era. The volcanic activity that had helped create favorable atmospheric conditions was simultaneously filling the atmosphere with gases that would eventually contribute to environmental instability. The high sea levels that had created extensive continental hunting grounds were fluctuating in ways that periodically disrupted established ecosystems and forced rapid adaptations. The climate systems that supported Azhdarchid prey populations were becoming increasingly volatile as the Cretaceous drew to a close. Temperature fluctuations, changing precipitation patterns, and shifting seasonal cycles would have challenged even the most adaptable predators, as traditional prey distributions became unpredictable. The asteroid impact that ultimately ended Ashdarshid dominance represented just the final catastrophe in a series of environmental challenges that had been building throughout the later Cretaceous. The creatures that had evolved to exploit the opportunities provided by late Mesozoic conditions were also vulnerable to the instabilities inherent in those same systems. The collapse of primary productivity that followed the impact eliminated the herbivore populations that formed the foundation of Ashdarshid food webs. The climate disruptions and habitat destruction that characterized the immediate post-impact period made flight capabilities irrelevant. There was simply nowhere to fly to escape the global environmental disaster. The speed with which these remarkable creatures disappeared from the fossil record testified to how completely their world had been destroyed. Ecosystems that had supported giant aerial predators for millions of years were eliminated within decades or centuries of the impact event, leaving no refugia where Ashdarshid populations might have survived the crisis. The permanent nature of this extinction highlighted the specialized character of Ashdarshid adaptations. Unlike some dinosaur lineages that left descendants in the form of modern birds, pterosaurs as a group vanished completely from the planet. The ecological niche of giant aerial terrestrial predators has remained empty ever since, despite numerous opportunities for other animal groups to evolve similar capabilities. This evolutionary vacancy serves as a powerful reminder of how difficult it is to achieve the complex integration of adaptations necessary for aerial gigantism. The combination of structural innovations, physiological specializations, and behavioral sophistication that made Ashdarshids possible represented such a specific evolutionary solution that it has never been replicated in subsequent radiations. From those first mysterious wing bones scattered across the Texas Badlands to the sophisticated aerial predators revealed through decades of patient scientific investigation, the transformation of Quetzalcoatlus from enigma to understanding represents one of the most remarkable journeys in paleontological history. These magnificent creatures remind us that evolution is capable of solutions that push the very boundaries of what we consider possible. Giants that once ruled both land and sky with capabilities that dwarf anything in our modern world. The story isn't over, though. Every new analytical technique, every fresh discovery, every innovative approach continues to unlock secrets that have been hidden for 68 million years, proving that even the most famous fossils can still surprise us with revelations that challenge everything we think we know about life itself.